What is going on, everybody? Today we're going to be talking about Actuary Level 1. So, an actuary is usually someone that goes into an insurance field, and they will kind of take over three main roles in an insurance company. They will be like predictive modeling, reserving, or pricing. So predictive modeling is pretty self-explanatory. Predictive modeling is try to predict shit with models. Pretty simple. Reserving is in essence making sure that the insurance company has enough money to pay out possible claims. So in other words, they'll look at like the likelihood of claims coming in the future, stuff like that. Look at how much money the insurance company has, how much money they're going to be having in the future, and ensuring that the insurance company can pay out all the claims if they were to happen, like that they have enough money that you won't just get scammed. So that's reserving. And then pricing would be determining how much to charge someone for a premium based on all these different factors. If you're going to get like a car, if you're getting car insurance, it'd be like how many crashes you have on your record. Do you have a shit ton of speeding tickets or whatnot? Like, are you a good driver? That kind of essence. And then determining how much to charge you for a premium to insure that car. So that's pretty much what an actuary is on a very, very like straightforward, very surface level. That's what an actuary is. Actuaries have around 10 exams that they have to pass in order to become a maxed out actuary, I guess you would say. So that's why I'm saying levels. Each exam is a level. The first two actuarial exams that every actuary will take is exams FM and exams P. But after that, either you choose to go into a life or health path where you continue on your education and exams through the SOA, or you choose to go to property and casualty and you'll continue exams through the CAS. There's also a lot of different things that you can do, like there's reinsurance, which is pretty much effectively insurance for insurance companies, or you can go into like very specific like niche actuarial roles at like companies that usually wouldn't have an actuary, where you are like the only actuary there and you provide all the actuarial knowledge, kind of stuff like that. You can pretty much do anything with this like career path, anything you want. It kind of ties into a lot of different things. You have a very strong background knowledge on a lot of different topics in the financial world, like in the business world. So it kind of like stems off into many different things, many different possibilities that you can go into. Primary like pipeline is through straight to insurance. So probably what I'll be doing. Either way, Actuary Level 1, we're going to be covering exam FM, or exam financial mathematics. Now, this is because this is the first one I have taken. It's not the first one you have to take. You can technically take P before FM. However, FM is kind of the main one, like the main learning curve of learning how to study for an exam. As P, you can kind of pass without necessarily studying as hard as you should be for an exam. FM, you do have to study for exactly how hard. This bitch is hard. You have to study for a long ass time. I think like the recommended hours amount of studying for an exam is like 500 hours per exam or something. It is a lot of studying, but it also is pretty rewarding. I think it's pretty cool being like knowing that I can do this, like knowing how all these different cash flows work and whatnot, just for exam FM, for example. I think that's really cool. I know a lot of people don't think that's really cool, but I think that's really cool, and I want to share it with you guys because it is what I'm going to be doing for probably the rest of my life. So, and I do enjoy it. I do love it a lot. So kind of want to just show it with you guys. I just want to go and say this does not count for any study materials. This is literally just a guy explaining kind of the very basics, just kind of introducing you to this sort of math. This by no means should count as your study materials. I highly recommend going to Coaching Actuaries or Infinite Actuaries to get your study materials. They are my two favorite, and it's worth noting Infinite Actuaries has exam FM and exam P for free. You can get the study materials for an infinite amount of time for free. So I would highly recommend, if you are interested at all or you are studying for an exam, go to Infinite Actuaries. They're free. So yeah, let's dive into exam FM. So there's three main things that we're going to start off with, and we're going to start off with an interest rate. It's also worth noting that the ideology of time value of money is also very important to understanding this course. And the time value of money is, in essence, just understanding that inflation is real. If you have a $100 bill, a year from now, that $100 bill will be technically worth less value, even though that still is $100 because the dollar is worth less. So that brings in the ideology of interest, where if our money is able to accumulate at a rate faster than it is able to depreciate through inflation, then we will technically be gaining money over time, and or we will be covering our losses of the inflation. So that kind of just is the concept of time value of money. It is knowing that money loses value over time, and in order to combat that, you need to invest in some way in order to combat that, or keeping a bunch of dollar bills in your mattress is just losing you money over time, compared to keeping all those dollar bills into something like a fund. I don't know, anything gaining you more money is better than losing money, Really weird way of saying it. I hope that makes sense. Starting off, we have the accumulation function. This is kind of like the backbone of all accumulation and discounting. It's like the backbone of all of financial mathematics. Now, we have two different types of interest rates. We have an effective interest rate and a nominal interest rate. An effective interest rate is going to be denoted I, and a nominal interest rate is going to be denoted IN. So this is not I to whatever I to the n. This is just a notation. This n is just signifying how many times this interest rate is getting compounded per year, and then an effective interest rate is just one compound per year. So let's look into how how the accumulation function and how they intersect, how they correlate with each other. So the accumulation function is going to equal 1 plus I to the t, to the t. Now, this is considered compound interest. Compound interest is compounded, essentially, or it grows at an exponential rate. So if you look at this, it would technically, if we're growing at a 5% interest rate, it would be 105% times 105% times 105% times 105%, however many years that we're going into the future. Now, if we look at it in terms of a nominal interest rate, so a nominal interest rate would be considered for like a semi-annual, if you have semi-annual payments, monthly payments, daily payments, anything like that, it would be this. And N is going to denote how many payments per year that is. So if it's semi-annual, there's 2, daily is 365, weekly is 52, quarterly is 4. You get what I'm putting down. And it's the same ideology that we have with this compound interest here, where it is 1 plus the nominal interest rate divided by how many times that is getting compounded a year. So if it's semi-annually, it would be divided by 2 because it's 2 payments per year, and then you raise it to however many payments that year, how many payments in total. So it would be the amount of payments per year times the amount of years. So in essence, if this is a semi-annual payment for 10 years, it'd be 1 plus the nominal interest rate divided by 2. All of that to 2 times 10. That would be exponent, or 20. So yeah, that's the accumulation function in terms of compound interest. So now if we were to look at simple interest, all right, now that I've properly labeled them, simple interest, so this is compound interest. Simple interest is simply going to be 1 plus I times t. Now, as you can see, compound interest, since it's compounding yearly, it grows at an exponential rate, as simple is linear growth. Simple interest, you barely use it. It's not really used in anything. It's kind of just a thing. And it's because compound interest will always gain, in terms of the accumulation function, the accumulation function of compound interest will always be greater than simple interest if the time is greater than a year. If the time is exactly 1 year, simple interest and compound interest will be the exact same. They will be identical, they will be equal, and it's because A of t is just going to be 1 plus I. 1 plus I. So at time 1, simple and compound interest are technically equal. However, anything beyond time 1, compound interest will accumulate at a faster rate than simple interest. And anything before time 1, simple interest will accumulate at a faster rate than compound interest, because it's linear and compound interest is exponential. So it has that half U type ordeal going on. So while it's dipping down in the U, simple interest is just going straight up and then eventually passes it at time 1. Compound interest soars way above it, and simple interest wishes that it could be compounded. That's kind of simple interest and compound interest. Simple interest, you barely ever use it. I'm not gonna lie. You will always assume compound interest unless the question states otherwise, unless it says explicitly in the question, this is a simple interest rate. You will use compound interest. Simple interest is never assumed. Always assume compound. So now with these interest rates, you would think that there's a way to convert an effective interest rate to a nominal interest rate, which there is. So this is how you would convert an effective interest rate to a nominal interest rate, or a nominal interest rate to an effective interest rate. Very simple. We're pretty effectively just taking these two and putting them equal to each other. The main point of this is the effective interest rate and the nominal interest rate are not equal. If you are given a 10% effective interest rate, that would mean you have to put the effective interest rate into here to then solve for the nominal interest rate. They are not equal. They're two completely different things. They're almost equal, but they're just off to the point where you will get every question wrong if you assume that nominal interest and effective interest are equal. So if the question says an effective interest rate and you need to convert it to a semi-annual rate, you have to do this. You can't just divide the effective interest rate by n and raise it to the n power. Just keep that in mind. These are two different rates, and this is how you would convert in between them. That's pretty much it for interest. I mean, there's not really much else to cover in interest. Pretty self-explanatory, pretty simple, very basic stuff here. So let's move on to discounting. All right. So now that we're looking at a discount rate, we have to take into account a discount factor, which is going to be denoted V. The effective discount rate, I forgot to write effective, but the effective discount rate is going to be denoted D, just like how I was denoted for the effective interest rate. And following suit, the nominal discount rate is going to be denoted dn. Again, this is not an exponent. This is literally just a notation to signify how many times this nominal interest rate is getting compounded per year. The effective discount rate and the nominal discount rate are two completely different rates. They're pretty similar to each other, but they are off just enough to where you will get every question wrong if you assume that they are the same thing. So I'll do that. If we look at a discount factor in terms of the accumulation function, it is this. V T is literally just going to be, you just divide by the accumulation function, kind of, and that's the discount function. In essence, if we just put t here, vt, this is going to equal 1 plus I to the t, or it can equal, these are all the same thing effectively, but this is what the discount factor is in terms of I. So now that we have this in terms of I, let's start thinking about it in terms of D, or what a discount rate would be. So if we kind of just follow suit of the interest rate in the accumulation function here, we kind of get these equations where the discount factor is equal to 1 minus the effective discount rate raised to the t. So as you can see here, this is very similar to interest and the accumulation function. It's just 1 minus d instead of 1 plus I, both raised to the t. They both equal a thing that we would multiply a number by to get its value at a different point in time. And then following suit, if this is the effective discount rate, if we follow the rules of what a nominal interest rate and an interest rate are, we would get this, the exact same thing, besides it's now the relationship is 1 minus d instead of 1 plus I, 1 minus d, dn divided by I to the n times t. And from this, we can get the conversion for a nominal discount rate and an effective discount rate being same thing as you would expect. It is 1 minus d equal to 1 minus the nominal discount rate divided by n to the n. Same thing as the interest rate, same ideology, same concepts here, just 1 minus d. And now we can start to kind of understand this a little bit better now that we have some of these equations up. So a discount rate is, you're literally just dividing by the accumulation function. So this is how, like, an accumulation function you would use to accumulate or find the value of something at a point farther in time, like later in time. As the discount factor, you would use pretty much identically to how the accumulation function would be used, in the sense of, if you're discounting $100, you would just do 100 V to however many years you're discounting. From this relationship of V being 1 divided by the accumulation factor, we can then find how a discount rate is in relation to an interest rate. So So these are our equations for how we can convert a discount rate to a interest rate or an interest rate to a discount rate. So the way I think about this is in the problem, you will be given either a discount rate or an interest rate. You can only use one or the other. You can't use D to find D. So that is why we have the equation set up like this. And then the way I think about these equations, which just helps me memorize them, is to get the interest rate, we have the discount rate and we accumulate it. We accumulate the discount rate to get an interest rate, or we discount the interest rate to get the discount rate. We also get that A of t, the way that we can accumulate using a discount rate is we use our equation for the discount rate, 1 minus D, and we raise it to the negative T. Because if we were to raise it as just a normal T, we're then getting V, but V is the inverse, no. The V is, they have this relationship with the accumulation function. So that would in turn mean that the accumulation function is 1 minus D to the negative T. These are kind of all the equations that you would need for a discount rate. It is the discount factor in terms of I, the discount factor in terms of D, how you can convert effective discount rate to a nominal discount rate, how you convert a discount rate to an interest rate, and how you can accumulate using a discount rate. So these are pretty much all the equations that you will use in your work, I guess. I don't know. There is one more way that we can accumulate and or discount, and that is with the force of interest. Yeah, so the force of interest is going to be denoted by the Greek letter delta. I don't know why. It just is. The force of interest, I'm not going to lie, is the bane of my existence. I hate the force of interest. It is so far the only thing that I have discovered in the actuarial pathway that I genuinely hate. Fuck the force of interest. This thing, we'll get into why it can be very annoying and very tedious to solve problems involving the force of interest, but I'm not gonna lie, force of interest is either hit or miss. Either the problem is really easy and it's just like the other ones, like with the interest rate and the discount rate, where it's like not really that big of a deal, but then there's other problems where it is now the hardest thing I've ever had to do using math. Very wide range on the level of difficulty coming out of force of interest. So let's get into it. So the force of interest in terms of, we'll write it in terms of the accumulation function and the discount function here. Pretty self-explanatory, pretty simple stuff going on here. The force of interest, if you want to accumulate it, it's going to be e to the force, or e to the delta t. Pretty self-explanatory. That's how you would accumulate it with. And then if you want to discount, it is then e to the negative delta t. Very self-explanatory. They're pretty similar, pretty like one is one. You understand this relation. This is the easy part. This is the easy ones. If you get a question involving force of interest and you can use these equations, you got luck. This is the easy part. So now if we were to look at the part that can then burn your bridges, is delta is also going to equal the derivative of the accumulation function divided by the accumulation function. This is a important thing to note because every once in a while you will get a problem that has this. Now this won't be it exactly, but you will kind of see what's happening here. So delta is going to equal the derivative of a of t divided by a of t. So if we are given in the problem that delta is equal to this, the derivative of t plus 1 is 1. So that's a possible A of t. So it's kind of just like, you see how that can like correlate with each other, and it's simple. But that's just one example of how you might use this equation. But there's also this equation. So that in of itself, I'm not gonna lie, I barely use this. This is probably my least used equation in all of FM. But it is an equation and there are questions on it and it is important to know. So if this is like the perfect world for an force of interest, this is like almost perfect because it's harder to work with this than this, but at least you don't have to do this final. Now, if you are given an equation for the force of interest, for example, if you are given something like this, where delta is equal to 0.02 plus 0.001 times t, you would then have to take the integral of this to then find the true value of delta, with the bounds being t. You would do it with respect to t, but then after that, it's the same ideology of here. You just raise it to the e. But the main point is that you have to take an integral. So if you are given an equation to find find the accumulation function, you then have to take the integral of that equation with respect to the time of which you need that equation. In essence, if you're investing $100 at time, like if you're investing $100 now and you want to see what it accumulates to in 10 years, you would take the integral of this with the bounds being 0 and 10, and then that would be, you do e to whatever that is equal to, and that would be your accumulation function. Now, where this kind of gets more involved with the bounds being actually important is if you are investing in the middle of time. So say you are investing at time 5, but you still want to know what that investment at time 5 is going to accumulate at the end of time 10. Your lower bound is going to be 5 and your upper bound is going to be 10. Now, this is important because in this scenario, you would not make your lower bound 0 and your upper bound 5 because that's like the amount of time that you're doing it. No, you have to keep that perspective of time consistent throughout the entirety of this. Really annoying. It's just kind of annoying. Not to mention that you have to take the integral, so it's calculus. But yeah, this is the force of interest. This is kind of just like in a very broad sense of what's going on with the force of interest. Yeah, but that's force of interest. In a sense, it's very easy, but applying this to actual problems is damn near impossible until you've practice with it a bunch. So I would recommend, if you are just now starting off studying FM in that first area of time value, first section of time value of money, I would highly recommend spending a lot of your time using doing force of interest problems, because it will take a lot longer for you to fully understand and fully grasp than compound interest and compounding discounts. Yeah, it's a lot harder of a concept. But I just wanted to include some more equations about the force of interest. So the force of interest is going to equal the natural log of 1 plus I, and it's also going to equal the natural log of 1 minus d to the first. Literally the natural log of a of t, or the accumulation function, if you see it as the same way I do. Or you could set the accumulation functions equal to each other, and you could get 1 plus I is equal to e delta. I mean, I guess technically we don't have any t's, so none of these t's would exist. But 1 plus I is going to be equal to e to the delta. 1 minus d to the negative first is going to be e to the delta. And then if we're discounting, 1 plus I to the negative 1 is going to be e to the negative delta, or 1 minus d is going to be e to the negative delta. So these are just kind of some equations that we use just for converting and whatnot from discount rates, interest rates, into the force of interest. That is our third and final way that or versions of our accumulation function that we might use. So now let's look at some example problems just to kind of show you how you might be using these in an actual exam. So we have a pretty standard, this is pretty much word for word what you would see for an example of for a question about FM. So yeah, let's take a look. You invest $100 into a fund that grants you an 8% nominal interest rate compounded semi-annually. What is the final value of your investment at the end of 20 years? One thing that any course, any study material, any actuarial professor, they will always teach you on FM how to write time diagrams. Time diagrams is a very important aspect of FM, and it really helps you understand what's going on with the cash flows and whatnot. It doesn't really help out. I'm not gonna lie, timelines don't help out at all pretty much in these early stages of financial mathematics, where we're just kind of we have one cash flow and we're accumulating it or discounting it to a certain point in time. It doesn't really matter in this aspect, but later on, once we get into a stream of cash flows, say we have a bond, say we have annuity, and then we have another payment at the end of this annuity that has a bunch of that's a shit ton more than the annuity, we would then want to draw a time timeline to see kind of how these cash flows work, and it would just kind of help us get a better understanding of where our equations. You'll have a way better understanding of what I'm trying to say once we get to annuities and loans and shit like that, where we actually use the timeline and the time diagram other than just to signify that we're accumulating or discounting. Let's get into it. So first off, we're going to start as always, with our time diagram. So the easiest ways to do this is we're starting at time 0. We're investing $100, so minus 100, and we are getting back X at 20. So what's happening here is we are accumulating, dot, 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 and then we're accumulating. So we're accumulating $100 20 years. So in essence, this would then be, so we're starting off with $100 and we're accumulating it 20 years. So this would be our first starting equation here. We start off with 100 and we're multiplying it by the accumulation function with time being, with t being 20 because we're accumulating to time 20. So this would then be this, if we were to actually write out what the accumulation function is going to equal in this essence, it is going to equal 1 plus 8% because it is a nominal. We're using a nominal interest rate here, so it's going to be 8% divided by 2 raised to the like 2 because there's semi-annual payments, and then times 20 for 20 years for 40 total payments. So that's going to be what our accumulation function is going to equal. From there, we would simply literally just put this into our calculator. So if you were to just simply put this into your calculator, you would end up getting 480.1. If you invest $100 into a fund that grants you an 8% nominal interest rate compounded semi-annually, at the end of 20 years, that $100 will now be $480. Pretty cool. That's how you would do it. It is worth noting that when you are solving these problems, never round. Rounding should be your very last possible resort. Literally, like, if you need to avoid rounding at all costs, because later on when you get multiple cash flows, very big numbers, very, like, they say we have, instead of semi-annually, we're compounding daily. It is very important to make sure that you do not round any intermediate calculation. Only round the final answer. That is a very important thing, or else if you do round your intermediate calculations, we'll get everything wrong. Like, if you were to calculate this out, say you did 4%, or say you did 8% divided by 2, you got 4%, you added 1 to it, so now you're at 104%, and you raise that to the 40th power, and you get whatever you got, and then you then round that number and multiply it by 100, you probably will not be getting 480. You might be, but that's kind of the ideology. You need to not round any intermediate calculation. But yeah, that's how a kind of a very basic interest problem works. This is probably like a 2 or a 3, probably a 2, not gonna lie. I would say high end 1, low end 2 level difficulty problem out of 6, or out of 10, I mean. So this is a very simple problem. Put this into perspective. This I would say is a very easy 2 difficulty. You need a 6 difficulty to pass. But yeah, that's a problem for interest. Now let's look at a problem where we're discounting instead of accumulating. All right. So we have a very basic discounting problem here, and which is you have to pay $100 in 20 years. You invest X into a fund earning 8% effective interest, rate today in order to cover your $100 in 20 years. Find X. So pretty much what we're doing is we are getting $100 here and we are investing X. And from here, we are going to be discounting. Discount. So we'll be discounting $100 back 20 years. So there's multiple ways of doing this. Now, this is one of the things I love about financial mathematics is there are so many different ways that you can solve every single problem. Since technically we are assuming that the interest rate is level, meaning the interest rate does not change throughout time, we can technically, if we wanted to, we can discount this 100, we can discount it 40 years and then accumulate it 20 years to get 0, to get it at time 0. Or we can accumulate it 20 years and then discount 40 years. We can do any combination of accumulation or discounting as long as we end up at time 0. Now, this follows through to the end of the course. Like, when we start talking about annuities and bonds, the equations that you will use to solve, like, to find the value of an annuity or a bond, will give the value at a specific point in time, but then you can then discount or accumulate that value at that point in time to a different point in time. So say if we have a stream of cash flows, we want the value of it at 20, we can find the value of the stream of cash flows at time 0 and then accumulate it to 20. All in all, there is a bazillion different ways of solving every single FM problem in existence, basically. So if my way of solving it, or if your study material's way of solving it is not the way that you solved it, does not matter. As long as you get the same answer, that's all that really matters. So from this, the most self-explanatory way of going into this would be doing this. Starting off with 100, and we're going to discount it 20 years. So this is then going to become 100. And then if we plug in the equation for V, we get 1 minus D1. So now we have D, but they gave us I. Luckily, they gave us the effective, I thought effective wrong. Oh well. Luckily, they gave us the effective interest rate, so we can then convert the nominal or effective discount rate very easily. We won't have to convert it. We won't have to convert the nominal interest rate into the effective interest rate to then convert it into a discount rate. We just already are given the effective interest rate, so we are able to do this equation. D is going to equal I divided by 1 plus I, or it's going to equal 8% divided by 1 plus 8%. This is then going to equal 7.4074%. Again, this is rounded. Number goes on forever, but you do not round the intermediate calculations. I only rounded this final answer. And when I go do this problem, I'm going to go back into my calculator, select this value, like this answer value, and then plug it in for D. Or I'm going to store this value for something and then plug, and then, do that. I'm not going to just write this value in my calc. I'm going to get the actual true value of this that is stored into my calculator somewhere, and I'm going to plug that in for D. I'm not going to just put in 7.0474 because my answer might be wrong because of the rounding error. You see what I mean? Do not round intermediate calculation. This is simply rounded so you can know if you got the right answer. But yeah, so then we simply just plug this in for D. So if we put that into our calculator, if we plug what the true D is in for D, and we put this into our calculator, there we go, we will get 21.45. If we have a liability of $100 in 20 years at a 8% effective interest rate, we need to invest $21.45, which will then accumulate to be $100 in 20 years. So that is one way of solving this problem. I also want to show you in this way we got the answer by converting the interest rate into a discount rate. I want to now solve this problem only using the interest rate. Starting off with our first equation, we have 100V to the 20th, and now we are going to write V as 1 plus I to the negative T. So this is just a different way of writing this exact same value. As you can see, they're both 100V to the 20th. So now with this, we don't have to convert I into D because we have I. It is given to us directly. So we can then just plug that into our calculator. So plugging this into our calculator, we literally get the exact same value as before. Even much so to the point where they are all the decimals I can see are the exact same. So these two, they're both the exact same way of solving this problem. These are probably the two most mainstream ways. If you want to know my personal favorite, it is this. I prioritize I over everything. It just works better in my mind like that. Whenever I have to use D in an equation, I will literally just plug this fraction in on my calculator and calculate it that way. I love the interest rates. My mind works in interest rates. It does not work in discount rate. However, your mind might work in discount rates. It doesn't matter. They're all different ways of solving the exact same problem. And as you can see, they all come out to be the exact same if you introduce no rounding error. Now let's look at one more example here where we look at force of interest. So pretty simple, pretty similar to our problem we had with the interest rates. You invest $100 into a fund earning 6% compounded continuously. What is the final value of your investment in 20 years? Again, we're going to start off with our timeline. As always, we are investing $100 and we're getting back, boom, timeline. Now, what are we doing? We're accumulating $100, accumulating. As you can see with pretty much all the timelines I've drawn in this section of practice problems, they are pretty useless. Like I was saying before, however, they will see more and more benefit as we go along deeper into this course. So I highly recommend, if you are doing any of these problems, get into the habit of always writing a time diagram. It is very helpful, very important, and it literally takes 30 seconds at most. So we're going to start off how we always start off. We are accumulating $100, so we're starting off with 100, and now we are gaining 6% compounded continuously. So it being compounded continuously means that it's going to be force of interest. So we would then just have a 20 like before, and then since like the accumulation function is compounding continuously, we're going to have to use the force of interest accumulation function equation, which is simply just 100 e to the force of interest times t, which if we then put this into our calculator, we get 332.01. So as you can see, this is very, all in all, this is just kind of like the first big major section of financial mathematics. This would be section 1, or the time value of money section, usually in the study materials. It pretty much is just covering very basic accumulation, very basic discounting, introducing force of interest along with an interest rate and a discount rate. Very simple, very basic, but it is very important when you are going through and studying these for yourself. The first 2 sections, the time value of money and annuities, I would say are 99.9% of the entire rest of the course. If you know for a fact, like if you are the best person in the world at calculating time value of money problems and annuity problems, you will also be the best person in the world at calculating loan problems, bond problems, immune is no immune. You get what I'm trying to say. Immunization. Immunize. Fuck. Immune. When we get later on, yeah. So that's section 1. I hope I wasn't too boring, but yeah, let's get into annuities. Now we're moving on to what is widely referred to as section 2 of financial mathematics, and that is annuities. So basically what an annuity is a stream of cash flows. So if we just have an example here, this is going to be our timeline. So this is our timeline, this is our time diagram. So now instead of us having one payment of 100 right here, what if we have a payment of 100 at every single one? So every single year, past year, like every single year, we get $100. So this would resemble something like a car payment. It's important to know that an annuity, you also have to have level payments. So that's why the 100 will all be values of 100 at each payment. In other words, an annuity is able to, where before we were able to find the value of one cash flow back at any point in time, with an annuity, we are able to find the value of any cash flows, like any sequence of cash flows. So here we have a shit ton, we have 20 cash flows, and we can evaluate it at time 0. Like if you think about it, if we were to write this out, it would end up being, so I was kind of using them before, but it's important to know that PV represents the present value and the FV represents the future value or the final value. It can go either way, it doesn't really matter. All that matters is that FV is the end, PV is the beginning. So if we were to find the present value, which means we want to find the value of this stream of cash flows at time 0, because the present is 0, then it would look something sort of like this. The present value of this stream of cash flows, it would be an equation kind of like this. We would discount this 100 back 1 year, then we would discount this 100 back 2 years, and then we would count the 3rd year, discount it back, add the 4th year, discount it back, all the way up until we add the 20th year, but we're discounting the 20th year back 20 years because we want the present value. So we want the value of this at time 0. So that's why it would end up just being like this. So from this equation, there's actually some really cool stuff that you can do. I'm not going to show you it right now because it's very confusing and takes a lot of time to explain. So if you really care about this course, you should do this on your own, but I'm just kind of going to tell you the end result of how we solve this, because I'm just trying to show you kind of what the math is about. I'm not really trying to prove to you that this math works. So then instead of writing this out, all this comes out to, this is going to be equivalent to what we would denote as actuaries as A angle N. So that's what it's denoted as. N meaning 20, I is the interest rate. In other words, this would be, the PV would be a 20, A angle 20. Yeah, this is just kind of like the basic notation of an annuity, just kind of like introducing what an annuity is and how it works. So I'm going to keep present value and future value up there just because they're important. In that example, this notation would have represented an annuity immediate, and it would have represented the present value of an annuity immediate. Now is kind of where we would introduce the difference between an annuity immediate and what is going to be known as an annuity due. So there's two main types of annuities. It is an annuity immediate and an annuity due. The annuity immediate is denoted A angle N, and the annuity due is denoted A dot angle N, and there's literally, let me make them a little bigger, there's literally just two dots above the A, and that's how you determine if it's angle or immediate annuity due or annuity immediate or annuity due. So now it's kind of like important to know what's the difference between an annuity immediate and annuity due. So what I'm going to end up doing is explaining it in a little bit. These both solve for the present value of an annuity immediate or an annuity due, meaning that they are giving the value at, or if we'll have a timeline down here. An annuity immediate, if this is our stream of cash flows right here, so 100, 100, 100. So imagine this is our stream of cash flows. An annuity immediate is always going to find the present value of this stream of cash flows one period before that, like the cash flows start. So an annuity immediate is going to find the present value of the annuity at this point, one period before. As an annuity due is going to find the present value at the point of the first payment. So an annuity due, if you solve for an annuity due, it's going to solve this annuity, even though they're the exact same annuity, they will just be solved at different points in time. If this is time 0, the annuity immediate is going to solve present value at time 0, where if you have this annuity and this is still time 0, the annuity due is going to solve for the present value at time 1. So what you can actually do with this relationship is you can have an annuity due is going to equal an annuity immediate discounted one period. So as you can see, So as you can see, the annuity due is equal to the annuity immediate discounted back one period. So now if we were to look at the future value of these, so the future value of an annuity immediate is going to be denoted S angle N, and then the future value of an annuity due is going to be denoted following the same like scheme here, S dot angle N. So now on our timeline, where these are going to line up is the future value for an annuity immediate is always going to find the value at the time of the very last payment. So S angle N is going to give you the value of this annuity at this point in time, where the annuity due, if you solve for the future value, or S dot angle N, it's going to solve for the future value of this annuity at this point in time. So then this also gives the relationship of the same thing that we have here, where the future value, or S angle N, is equal to S dot angle N times V, or discounted one period back. I know I didn't show any equations on like any of these. I will get to that in a little bit, but I just kind of wanted to show you this picture and paint kind of like what's going on, because these are all different notations, but they all do the same thing. They all find the value of this annuity at some point in time. So if this was the annuity, just N payments of 100, these are the places, if you were to solve for this annuity, these are the places, or these are the points in time where this equation would give that value. I hope that made sense. I confused myself, but you get it. You understand. Like it'll work better when you actually like see the examples and see like how they correlate with each other. But I just wanted to paint this picture before, just so you have this ideology of how this is going to work. And also just keep in mind, just because it gives an annuity due, so say in the example, say in like a problem, it says we have a annuity due of an annuity due with payments of 100. You don't have to use the annuity due present value to find that present value, or you don't have to use the annuity due to solve the future value. You can, if you want to, use the annuity immediate for the present and the future value if you want to. You just have to keep in mind that you are going to either have to accumulate or discount depending on where that value is going to end up. So just keep that in mind. If you are given an annuity due and you are given an interest rate and you're like, I don't want to convert the interest rate into a discount rate to solve for this annuity due, I'm going to solve for this in annuity immediate and then accumulate it one period forward, find the present value of the annuity due. Hopefully that made sense. Let's get into actually like what these equations are and how they play into each other. All right, so starting off with the first one that you should learn is going to be A angle N. So A angle N, if you remember, is the present value of an annuity immediate. This is going to equal 1 minus V to the N divided by I. Very simple. 1 minus V to the N divided by I. You will use this equation so often while doing this math, your mind will be blown. Like genuinely, if you study for this, you will use this equation so much to the point where it is like you have muscle memory in your calculator of you pushing the buttons in order to get this out. Like I have muscle memory. I could literally just close my eyes and go 1 minus 1.05 to the negative whatever divided by whatever. Easy. I've put it's a very important equation. Very important equation. Now, if we look at an annuity due or a dot angle N, it is going to follow the same premise of 1 minus V. However, it is just going to be divided by D instead of I. So an easy way to remember, like to correspond these equations with the annuities is an annuity immediate is divided by an I, an annuity due is divided by a D. Pretty simple. Other than that, they're the exact same equation. And if you remember, you literally just have to accumulate A angle N, one period to get A angle D, or discount A dot angle N, one period to get A angle N. These are the actual formulas. We'll write the comparison here. So now let's move on to the final or the present or future values of the annuity. So if we want the future value of an annuity immediate, we're going to have, if you remember, S angle N, and this is going to equal slightly different. The way that I think of these is that it's literally inverted, or another way that you can think of it is it'd be the accumulation factor minus 1, discount factor 1 minus the discount factor. However you want to think about it, these are the equations. I literally think about it as it's like the inverse. Just flip these two around, Vn and 1, and you get this. Very simple. But as you can see, the annuity immediate is always divided by I. So that is why you remember annuity immediate I. You divide by I. Now, if we just follow the trend of what's going on here, S dot angle N is going to be the same exact thing besides divided by a D, because it's annuity due, if you remember. So these are our 4 annuity equations. They solve for the future value or the present value of an annuity immediate or annuity due. Mind you, if you remember the time diagram I drew before, time is really just kind of perspective unless you're working with force of interest. So in that sense, if you really wanted to, let me write this too. If you really wanted to, like this is what I mean by you can solve it a million different ways, and because you kind of just find whatever way works for you, like whatever kind of way of systematically figuring this out works for you, which you develop just through literally just practice. But yeah, so these are the equations. In my personal opinion, I always solve for like I said before, I always work in I. My brain works in an interest rate. It doesn't work for the discount rate. So literally what I would do is I would either solve for an annuity immediate, the future value or the present value, and I would accumulate it one period forward if I needed to do, or what I would do if it was something like later on, like really soon actually, we're going to be learning about an increasing annuity. For that, we need to divide something by D. However, since I work in I literally just remember the equation, I divided by 1 plus I, and I told you I plugged that into my calculator whenever there's a D. That's just kind of my way of going about it. Everyone's going to have their own little way about solving all these problems. Like I said before, there's literally bazillions of ways to solve all these problems. So as long as you're getting the right answer, it kind of doesn't really matter how you get there, as long as you know if the way you get there makes sense. You can't just make up shit. You actually have to follow the rules. But as long as you're following the rules and you get to the right answer, you're doing it right. It doesn't matter that your work doesn't match the coaching actuaries one. I know that's a really good example of most of the time your work will never match up with coaching actuaries, which is really annoying because they always work through first principles. I do not. But yeah, coaching actuaries always approaches every question with first, I forgot how they call it, but I think it's like first value principles or something, and their solutions are always whack. So just a warning, if you pay for coaching actuaries instead of getting infinite actuaries. These are the equations for an annuity due, annuity annuity immediate, the present values and the future values. Very simple stuff. You will, by the end of studying for FM, know all of this by heart. I don't think you'll ever forget it. So now there's just a little, just to kind of prove to you that you can literally solve this however you want. So these problems however you want. Just to kind of like add to the cherry on top, if you have an annuity immediate, right? So we have the present value of an annuity immediate, A angle N. If we accumulate this N years, we will get S A angle N. Or in other words, if we accumulate the present value of an annuity N years, we get the future value of that annuity. Who would have thought? Now this also works vice versa in the sense of the future value. If you discount it back N periods, you will get the future value. And the same thing works with the annuity dues and the annuity, literally with the annuity dues. So literally you have these pairings where you can literally just, like, this is what I mean. You can just solve for the value of whatever you're trying to solve, like whatever you need the value of, you can solve for that value at any point in time and then just move that value to wherever you need it to go. With level payments, which is required for an annuity by definition, these will always hold, and this is how you would interchange any of them. So yeah, these are really, it's really kind of confusing at first, just kind of like, I know it's very hard to like look at and be like, there's no way that this is math. Like if we take a seat and we analyze what's going on this whiteboard, there's one singular number, and that number is 1. There's one number on this entire whiteboard, and this is about 75% of the entirety of the annuity section. Isn't that crazy? So yeah, this is pretty much annuities. This is very basic. Now, this is under the time assumption that there are one payment per year and N is each year. So now we're going to look at what would happen if there are like semi-annual payments or non-semi-annual payments. But I'm going to keep it real. This is what I do. So I wanted to kind of introduce a concept to you because all the annuity equations we were looking at before all would assume that there are yearly payments, but I want to look at in the case where there's not yearly payment. So what a lot of study material will teach you is something like this. This would be the notation. I have no idea how to say it, and I have no idea what it means. Just know that they will teach you this, and then it'll be also, they'll have these for all the corresponding ones. So it'd be A angle N, A dot angle N, S angle N, S dot angle N. It'd be the same thing, and they all just mean that it is N years and then M times per N year. But instead of, here, I'll just write all of them out. So yeah, so these would be the notations for all of them. But I'm going to show you exactly how I would avoid doing this and just use the equations we had before. We're going to look at A angle N just for reference. So I just kind of wanted to show you guys how I would go about solving one of these if it were to be like a semi-annual payments or quarterly payments. I would simply multiply M by N, the amount of years by the amount of times each year, and I would get that number. So if it were to be, say it was, we'll actually look at an example. So if we were to look at an example kind of like this, where I'm just giving you the numbers, it would end up being A angle 40. So by the way, what all these numbers mean, since M is 2, that would mean we're compounding 2 times per year, and it's 20, so that means 20 years. So we have 40 total payments. And then the nominal interest rate is compounded semi-annually, 8%. So what we would end up having is A angle 40 is equal to 1 minus V 40 divided by 8% divided by 2. Now, V in this case, if you see I wrote off here, V is going to equal the discount rate for the nominal period. You know, you get what I'm putting down? So in this case, V is going to equal 1 plus 8% divided by 2 to the negative first. And then we would just plug this into our calculator and we would end up getting a value for A angle 40, which I'll do real quick. So if you were to put this into your calculator and you did it correctly, you should end up getting 19.7927. Then, or actually 7928. Sorry about that. Obviously it goes on forever, but it's rounded. So this is just in essence what I would end up doing. I'm going to be completely honest with you guys. I have no idea what these what the equations are for that. I have no idea anything about that. I just do this way if it is a different thing. And if they give me an effective interest rate, I will find the nominal interest rate and then do it that way. That's just kind of how I do it. Voice crack. But if you guys there are, like I was saying before, there's millions of ways of doing all these problems. This is just my personal way. If you do the study material and you find that you actually like these equations, go for it. Or power to you. Whatever way that you like better is the better way of solving it for you. So now we've looked at annuity, like the general equations for all the annuities, and we looked at how you would solve them if they were compounded not every year. So now there's one more case of annuities that we need to look at until we're done with annuities. Actually, there's two, because there's the force of interest annuities. We'll look at those later. Not even called annuities, but so now we're going to look at something called a varying annuity. Now, a varying annuity is something that either has increasing or decreasing payments. So this would be if you started with 100 and you were increasing 5 every subsequent payment. So it'd be payments of 100, 105, 110. That would be an increasing annuity. Or if it was the other way and it was payments of 100, 95, 90, that's a decreasing annuity. And you can't just use the normal equations that are given to you with these annuities. You can derive the formulas for the increasing and decreasing annuities from those formulas, like from the original annuity formulas, but I'm gonna just show you how to do it. There is an equation that is the perfect equation. It is called the P and Q equation. I don't know if that's the actual name. That's what I call it. That's what my one professor before called it. He called it the P and Q formula, but I've never been able to find this formula. But the P and Q formula is this is the P and Q formula. Now, in this case, P is going to be the starting amount, and Q is going to be the change in the payment. This is a general purpose formula that will solve for the present value of any varying annuity. P is going to be the starting payment. So if the starting payment is 100 and it's increasing by 5 every time, it's going to be 100 A angle 10 plus 5 divided by I angle NVN minus NVN. And then it worked the same way if the first payment's 100 and you're decreasing 5 every time. So it's payments of 100, 95, 90. It would be still PA angle N will still be 100 A angle N. It will now just be minus 5 divided by I A angle N minus NVN. So this is just a general purpose formula that will solve for the present value of any increasing annuity, as long as the increasing amount is the same. Like if it increases 5 every time. What I'm saying is this will not work for when an annuity, if the payments are increasing by a percentage every time. So if the payments are increasing by 3% every time, this will not work. However, if it's increasing by a steady amount every time, this will work. Now, there's a whole bunch of other ones. I'm going to show you the really important ones, the ones that I personally use, but I'm going to be completely honest with you. There's so many annuity formulas, so many different cheats and tricks that you can use to solve for annuities. All I'm saying is, as long as you know how to solve for if you know how to solve for the present value and the future value of an increasing annuity and the decreasing annuity, you will be fine. There will be other ones that are very complicated, but they're this. If you memorize this equation by heart, all increasing annuity problems will only take you 30 seconds. Cool. But now I have to remember a bazillion different equations. So this is just a general purpose formula. This will solve for the present value of any varying annuity. Now, if you want to solve for the future value of a varying annuity, what you can do is you can just solve for the present value and then accumulate it that many years forward. Same thing as before, where A angle N is, if you accumulate it N years, you get S angle N. Be the same thing here. If you accumulate whatever you get, you'll get the present value, final value of it. Now we're going to go into equations that are actually beneficial, because this is a very good general purpose where it's if you don't remember the equation, if you don't remember the right equation for that situation, if you know this, you'll still be okay. It might take you a little bit longer. It might suck to actually have to solve it, but you will be able to solve it. But with these equations I'm about to show you now, it will make this a lot simpler. You won't have to put in all these different things, but they are going to look pretty similar to this. Also, it's worth noting, again, this is a general purpose one. So this works both increasing and decreasing. The ones I'm about to show you only work for either increasing or either decreasing. So that is why this formula is a GOAT and the other ones aren't a GOAT, but the other ones are technically better because they're faster and they make a lot more sense. So an increasing annuity is going to be denoted, this is an annuity immediate, by the way. It's going to be denoted I angle N or IA angle N. And it is going to equal, this is going to solve for the present value of an increasing annuity. Now, if you wanted to solve for the future value of an increasing annuity, it's going to be, so the future value of an increasing annuity immediate is going to be denoted as IS angle N. And it is going to equal, so the future value of an increasing annuity immediate is going to be S dot angle N minus N divided by I, or very simply, it's going to be the present value accumulated in years. So I really wouldn't recommend committing this to memory. I would simply just know this and then know that you can accumulate it forward. Now, there is an increasing annuity an increasing annuity due. This is going to equal, I bet some of you could have guessed it, the same exact thing as the annuity immediate, just divided by D. Just keep in mind, annuity due, divide by D. Annuity immediate, divide by I. Applies for everything. And then it'd be the same thing here, where if you need to find S dot angle N, you would simply just accumulate I dot angle N here, or you could just do this equation. I'll write it down. So as you can see, the increasing annuity due is the same thing as the increasing annuity immediate, just divide by D, or you can accumulate the present value and years to get the final value. So this is all for increasing. However, if we were to flip over to a decreasing annuity, these would slightly change. However, this equation, like I was saying before, applies to everything. This equation will not change. An increasing annuity was denoted as IA angle N. So I wonder how a decreasing annuity is going to be denoted. So a decreasing annuity immediate is denoted DA angle N. Who would have thought? Who would have thunk? And this is going to equal, now, just like the increasing annuity immediate, I would commit this equation to memory, because if we commit this equation to memory rather than any of the other ones, same with the annuity immediate, or same with the increasing ones, because with this one, you can just divide by D instead of I to get the annuity or decreasing annuity due, or you can accumulate it n years to get either the increasing annuity or the final value of the decreasing annuity immediate, or you can divide by D and then accumulate it n years. So I'll just write those out real quick. So yeah, after writing all those out, they're the exact same thing as the dealing with an increasing annuity. Yeah, like the same premise. It's just the formula itself is changing. However, the same ideology of if it's due, you divide by D. If you want the future value, you just accumulate n years. Same ideology applies. So these are all the basic annuities. Now, there is a couple more types of annuities that I haven't really talked about, and that is because they involve the force of interest. If you have an annuity and it is compounded continuously, we denote it, I don't know how to say this. I'm not going to lie. I don't think I've ever said, I don't remember how to say this. I'm going to say A line angle N. But it's literally the same thing, but with a line above it. It simply just means it is an annuity that is compounded continuously, meaning we need the force of interest. Now, if you were following along, you should already be able to come up with what this is. But that's the equation. Just like the annuities, if it's annuity immediate, you divide by I. An annuity due, you divide by D. If it is an annuity that is continuously, that's compounded continuously, you divide by the force of interest. Very simple. It stays strong with all of them. And that same thing applies to if we need S or the future value. It would then just be, the future value is going to equal the same thing of the future values of the other annuities, just divided by the force of interest instead of I or D. So that's pretty simple. But now that we need to talk about a perpetuity. A perpetuity is if there are payments that go on forever. In all of the annuities I just showed you, there's n time periods. There's n periods. What I'm about to show you is there are no periods. In other words, n is infinite. We simply denote it as a angle infinity. And this is going to equal 1 over I. Very simple. Very simple. This is one of my favorite things in the world. It's literally just 1 over I. I'm not going to show you how it comes out to be 1 over I, but it comes out to be 1 over I. Now, if you have an annuity due, can you guess it? A dot angle infinity is going to equal 1 divided by D. Who would have thought? If it's an annuity immediate, you divide by I. If it's annuity due, you divide by D. Who would have thought? Who would have thunk? Now, what's kind of cool about these is that you technically, there is no future value because the payments go on forever. There is no future value, so you only will ever need to calculate the present value. So these are your equations for that. However, there are such things as an increasing perpetuity and a decreasing perpetuity. So I'll show you those right now. Actually, I lied. There is no such thing as a decreasing perpetuity because at a point, a decreasing perpetuity will be 0. We'll eventually have payments of 0, making it a finite number of payments, making it not a perpetuity. So a decreasing perpetuity does not exist. I just completely lied to you. But an increasing annuity or an increasing perpetuity immediate is going to be denoted as this, same thing as before, following those same concepts as before, where we literally just kind of sub in what we're doing. And this one's kind of tricky. It's going to be divided by ID. Now, if we have an annuity or perpetuity due, an increasing perpetuity due, it would be denoted as this, same thing as before. We just put that dots above the I, and it is going to equal 1 over D squared. With this being said, there are a couple more annuities. So if we have a varying continuous annuity, it is very rare. I have never seen a problem like this ever. However, it is a thing that you can get tested on. So I'm going to show you real quick. It's very simple. I'm not going to show you how you would get, like how this is derived, but I'm just going to show you the equations. So an increasing annuity that is compounded continuously is denoted IA with a bar over it, angle N. Still don't know how to say it. It's going to be pretty similar to what we were working with before in the sense of it's keeping the same thing. Besides, it's dividing by the force of interest instead of I or D. Now, if you're catching on, there's a very common theme. If it involves force of interest being compounded continuously or a perpetuity, actually not a perpetuity, if it involves being compounded continuously, you divide by the force of interest. If it is an annuity due, you divide by D. If it's an annuity immediate, you divide by I. The only situation where this doesn't happen is right here, where you divide by either I times D or D squared. This is the only one where that doesn't happen, just so you guys are aware. So now continuing this theme with the force of interest, I'm not going to write out the final value of this because I'm just going to write out IS with a bar over it, angle N is going to equal IA with a bar over it, angle N, accumulated N years. So you guys don't need to see that. You guys have seen that a couple of times now. But I will write down this one. For an increasing annuity that is compounded continuously or a decreasing annuity that is compounded continuously, these are the two equations. You'll notice they're slightly different than the previous ones. However, they follow the same ideologies. A angle N, besides this time we're having a bar over it, so it would be this one. So instead of angle or an annuity, the present value of an annuity due, and then you would divide by this by the force of interest. They follow the same, like I said, they follow the same concepts of an annuity minus NVN divided by whatever is like the interest or whatever the rate is, and the same with a decreasing, where it's N minus the present value of an annuity divided by that same. So in this sense, the only thing that's different is instead of annuity dues, we're using annuities that are compounded continuously. Yeah, that's the only variations, but it's a very slight variation. I will say the amount of times I've seen this in my life, I can count on my hand, on one hand, and I don't have to use any fingers. So that's how many times I've used this. That's how often it comes up. Take that with a grain of salt because they can and probably will test you on it. It's kind of just truly the amount of times I've seen a problem that uses this. is 0. I've never seen a problem that used this. So, but just know they can test you on it. It is a possibility. There's one final varying continuous annuity that we have to look at, and that is a varying continuous perpetuity. An increasing continuously compounded perpetuity is going to equal 1 divided by the force of interest squared. It's following the same ideologies up here, but now with force of interest. Now this one is unique because unlike this, it's not I or D. It's literally just the force of interest squared. And if you remember before, you can't have a future value of a perpetuity because the payments are infinite. You can pinpoint a value of the perpetuity at that point in time, but you can't find the end value of a perpetuity because there is no end value. It's infinite. It goes on forever. But yeah, so these are everything I just showed you is all of the annuity equations that have to do with level payments or level increase. What I mean by that is, or level decreases. What I mean by that is none of these, if the problem states that payments are increasing or decreasing by a percentage of the previous payment, none of these will work. None of these will work. These only work for payment, like level annuities and increasing or varying annuities that vary at like numbers, not percentages of the previous ones. So let's look at how to do those, I guess. All right, this is actually one of my favorite present values to calculate. I don't know why, I just really enjoy this, but it is denoted as GA angle N, and it's going to equal, this is the equation. GA angle N is going to equal 1 minus 1 plus R divided by 1 plus I to the N divided by I minus R. I in being the interest rate and R being the rate of change for that payment. For example, if the payments are increasing 3% every year, R is going to be equal to 3%. Yeah, this is the equation that you would use for it. It's actually my favorite equation. I'm not going to teach you like the annuity due and the other ones of it because you don't need it. Just use this one. This one's a lot easier to use. And if you remember the timeline, timeline I gave you before of the annuity immediate, present value, final value, and the annuity due, present value, final value, this will solve for the same time as an annuity immediate present value. So based on that, you would simply just accumulate, discount however many years to get to the time that you want. This is the only one you need. Before we move on to practice problems, I just want to say there are so many annuity tricks out there, like a bazillion. Like, I'm not joking. Every time I would study for FM and I would have something to do with it, like a question to do with annuities, I would always learn like something new about the annuities, like some new trick that makes you solve the problems faster, just new relationships that you never known before, just new different things that you learn, and you could only learn by doing problems. That's kind of why it requires such a long and demanding amount of studying, is because some of this stuff you're not as you can see, I just went over 80 different equations that all at the end of the day technically can compute the same thing. I just showed you about 20 different ways of computing the same thing, which is really annoying, but they're all in like different aspects and they all have different little factors that you have to count in. It's just very annoying and it's very tedious, but that is why you need to study for it. It's also why I think it's actually really cool to do, because where else are you going to find math like this? Nowhere. All right, so that's pretty much sums up annuities. That's all the equations you need to know. So let's work a couple practice problems. So our first problem here, you purchase an annuity due at time 3 for X. This annuity pays $100 every year, yielding a 8% effective interest rate. Find X. We're going to start off how we always start off every financial mathematics problem. And this is actually where you're going to start to see the beauty of some of these time diagram. I also didn't write how many years this was, so we're just going to put, sorry about the scuffness, but it's a 20-year annuity, just so we have that set in stone. This is going to be our timeline. As you can see, we need to add in the payments. So it's going to be annuity due, and the payments start, you purchase it at time 3, and it's annuity due. So that means you get a payment as soon as you purchase it. So that means payments of 100 are going to be like this: payment of 100, payment of 100, because it's a 20-year. Actually, there's not a payment of 100 here. I lied, because it's an annuity due. Here we have 20 payments of 100 on our timeline properly to scale. At time 3, we bought the annuity, and now we want to find X. It doesn't say in the problem, but I'm going to say that we want to find X at time 0, just because I want you to solve this for time 0, not time 3. But with this being said, we're going to have to solve for an annuity due, and we have to solve for this annuity. We have to solve for the present value of this annuity, discounted back a certain amount of years, depending on what we do use. Now, we have a couple options here. We can calculate the annuity due, and that would give us the present value at time 3, and then we can discount it back 3 years to get it to time 0, or we can calculate the present value of this annuity using an annuity immediate formula, giving us the present value at time 2, and then just discount it back 2 years. I'm going to do that because it gave us an interest rate, and an annuity immediate is a lot easier to work with if it gives you an interest rate compared to an annuity due. So I'm going to do that. So that means that our annuity immediate is going to give us the present value at time 2. We will then have to discount back 2 periods. So if we start off here, we have 100. That's our payments. We're using an annuity due. There's 20 payments, so N is going to be 20. So we have 100 A angle N, or 100 A angle 20, and then we're having to discount it back 2 years, so V squared. So this is actually going to equal, if you want to see it written out, it's going to be 1 minus V to the 20 divided by I V squared. Obviously, I didn't write in the variables here, but if you were to plug this into a calculator, you should be getting 841.75. So that means the present value of this stream of cash flows at time 0 is $841.75. Cool. So that's pretty much a very basic annuity problem. Let's look at another one. So if you buy a perpetuity for $1,000, if the effective interest rate is 6%, what are the payments of this perpetuity? If we start off strong, how we always do, can we draw our time diagram? We're going to get payments of X every year, all the way on forever. That's our time diagram. There's not really much else to it. There's not really much we can do. Pretty much we're trying to solve for X. If you remember our equation for the present value of a perpetuity, we're going to end up having 1,000, or the present value of the perpetuity is going to equal the payment divided by the interest rate. Or the present value is going to equal the payments divided by the interest rate. Or this is going to be 1,000 is going to equal X divided by 6%. Now it's worth noting, if the payments were not annual and they were semi-annual or quarterly, you would then have to convert this interest rate into that of effective interest rate for that period, and then divide by that, not by 6%. Just worth noting. Remember, interest rates, discount rates, force of interest is always for that period of time. So if the period is a half year, it's the interest rate for a half year. So then if you solve for X here, you will end up getting, if you solve for X, you will get that X is equal to 60. So that means, and you can even divide 60 by 6% and you'll get 1,000. But that means that with $1,000 at a 6% interest rate, technically you can get payments of 60 for the rest of the end of time. But that's kind of cool. That's a very basic perpetuity problem. Very simple. Let's look at one more annuity problem. You buy a 20-year annuity due with a starting payment of 10. Each subsequent payment is 3% higher than the last. At a 8% effective interest rate, calculate the final value of this annuity. With this one, we're going to have to use that GA formula that we had before. But first, like always, our time diagram. This is our time diagram. What's end up happening is going to be, we're getting 10 here, and then we're getting 10, and then 10, and then 10. But we are also here, we are getting 1 plus 3%. This is very hard to read. Okay. So this is our time diagram. It's kind of poor, I know, but it's whatever. So as you can see, we're getting payments of 10 every single time, but after the first payment, our payment of 10 is increasing by 1.03 or 3%. Our payment of 3 is increasing by 1.03 squared or 3% compounded. And then that just continues all the way up until the 20th payment, where it is going to be 10 times 1.03 compounded 19 times. This is our time diagram. This is just kind of goes to show why it is beneficial. I know I kind of wrote this poorly, but this is in essence what you would do. You would make this a lot better, and obviously you have a pencil so you can write a lot smaller. It just kind of sets up so you could visualize what's actually happening with these payments. It helps a lot with stuff like this. So now to actually solve it, our starting payment is going to be a payment of 10, and then the equation we're going to use is, if you remember, we're going to use the GA angle N for it, because that's the increasing one when it is increasing by a percentage rather than a set in stone amount every time. So then if we have this formula, I'll just write it here. So this would be our equation. It'd be 10 times 1 minus 1 plus r divided by 1 plus I to the n divided by I minus r, I being the interest rate, r being the rate of increase or decrease for each subsequent payment. So then if we just plug in what's going on here, so we get 10 times 1 minus 1.03 divided by 1.08, that raised to the 20th, and then all that is going to be divided by 0.08 minus 0.03. And if we put this into our calculator, this is going to equal, I'm going to write it up here, 122.50. So that's, if this is the present value of this annuity. However, actually, wait, it's annuity due. Whoa, I forgot I wrote annuity due. That's unfortunate. Nothing really changes too much. So this is what we got for the present value of this annuity. And if you remember this, since it is an annuity, this is counting for the present value of an annuity immediate. It is counting for one period behind the first payment, and the first payment is at time 0. So technically this is the present value of this annuity at time -1. And we need to find the present value of this annuity at time 20. Effectively, we increase it 21 periods. Yeah, we accumulate it 21 periods. So I'm like completely out of space on this whiteboard, so I'm just going to erase this part. But remember what I said before, no intermediate rounding. I'm going to get the value from my calculator when I do this later to find the final value, but this is the present value at time -1 of this annuity. Since we have that, this is the present value, I'm just going to write PV, and it's going to represent this. Just know that this value is the value of my calculator. I'm not actually rounding, because if I were to round, I would get the wrong answer. But yeah, we simply just accumulate this 20 periods. This is going to be PV times 1 plus I to the 21st. This will accumulate it from -1 to the 20th, time 20, where we want the value of this annuity. So this is going to be 122.51 plus 8% to the 21st, which is then going to equal, now what you should be getting is 616.65. That is the value of this annuity at time 20. It's the final value of this annuity. That's annuities. Annuities, honestly, is low-key the hardest part to learn about in financial mathematics, but it is very important. Literally, the rest of the course is annuities. It is the time value of money. It is kind of like introducing the background knowledge of an annuity, and then an annuity, you learn about what an annuity is, and then for the rest of the course, you use annuities to find out, or you find the values of really cool, unique annuities. So this is pretty much the backbone of all of financial mathematics, which is very hype, very steep learning curve. If you can perfect the first 2 sections of FM, you have inherently, in fact, perfected all of FM. So keep that in mind when you're studying. But yeah, that's the annuity section. Next, we have loans. Today we're going to be looking at loans. In particular for this section, loans are pretty cool. Loans are very similar to annuities in the sense of, if you need to find the value of a loan payments are pretty much an annuity if you think about it. But we'll get into that later. Before we get into loans, there's 2, like, kind of not really too important concepts. They're kind of like just common sense in a way, but they are something that you could be tested over. So I kind of want to just go over them right now. The NPV is going to represent the net present value, and pretty self-explanatory. Usually in these problems, you'll have a, it'll be like you'll have a system of cash flows, I guess I'm going to call it, where you have like some liabilities, some assets, pretty much basically throughout here. I'll just draw. So pretty much with a net present value, what we would do is we would analyze all these cash flows and find the net present value of these cash flows. And it's pretty self-explanatory. You would just discount this one back 1, discount this one back 2, discount this one back 3, discount this one back 4, whatever you're left with. Make sure if it's a negative, you're subtracting that. And if it's an addition, that means you're getting the money, like you're receiving the money as money's going away. So it's pretty simple. It's literally just kind of like an annuity, besides some of the payments are negative. So you just kind of find the net present value of all of these cash flows, very simple, very like intuitive. So then the next big thing that there is called, it's going to be the IRR, or the internal rate of return. This is going to be, again, pretty not self-explanatory, but it's very simple and it follows the lines of net present value. If we had our cash flows again, so if these are your cash flows, the net present value would be the present value of all these cash flows at time 0. This would be the net present value of the cash flow at time 0. So like I'll just write MPV. And then the IRR is going to be the rate of return to make the net present value of the cash flows equal to 0. Literally, like what I makes this values of cash flows 0. Yeah, that's pretty much it. Technically the equation for it is, all right, so this is the equation for it. The net present value is going to equal 0. And then while the net present value is equal to 0, you take the present value of all the cash flows, and the interest rate that will cause the net present value to be 0 is the IRR. Now, mind you, these two things both on your financial calculator, which you should have bought. Probably should have mentioned that at the very start of this, that a financial calculator is very important to this course. However, financial calculator literally has keys that do this for you. So it's kind of like, as long as you know like what is actually happening, like what the IRR and what the NPV means, you can solve it if you know how to do an annuity and how to do time value of money. So it's not really that big of a deal. They're just two concepts that are in the like syllabus for exam FM. They're not too important. Now we get to talk about loans. So loans, in a sense, are pretty similar to an annuity, where they are an annuity. You have level payments every however a long amount of time. It's an annuity. The only thing that's different about loans is that they go more in depth with what is called as an Either way, you go more in depth and you make kind of like this schedule that, like, you make this schedule that literally calculates out at each time. So yeah, I'll just write it down. And so we're going to start off strong. L is going to represent the loan amount, which is also going to equal OB0. OB0, or OB is going to stand for the outstanding balance. And then the number here represents the outstanding balance at that time. OB0 is the loan amount because you have yet to pay any payments. You haven't paid anything off. You haven't paid off any amount of the loan. So, and the loan hasn't accumulated any interest because it's at time 0. So it's the loan amount. And then the outstanding balance is just the balance that you have left to pay, or it's the balance that like grows interest. So yeah, so if you have $100 car payment and you need to pay off $1,000, interest rate is 9%. You'll pay off $10 of principal. The outstanding balance will go down $10. The other $90 will go to the 9% of interest charged on $1,000, and then the other 10 will go to reducing the outstanding balance. So very simple stuff. And then R is going to represent our payment. Usually with loans, the payments are level, but there will always be some form of an annuity, in the sense of it'll be an annuity, increasing, decreasing, or level payments. It'll be an annuity. R is going to represent our payments for that annuity. I is going to represent our interest paid for that specific time. I0 doesn't exist because there is no interest, but I1 is going to equal the outstanding balance at time 0 times I, and that's just the amount of interest that you have to pay. And then the other one, final one, is going to be principal paid. So principal paid is what's left over of the payment after it pays off the interest, or in a sense, it's R minus I, and the principal payment is what lowers the outstanding balance at each time. So as you can see, I, P, and OB I and P all are like in correspondent to time, where their value will change over time. Interest will go down, principal will go up, outstanding balance should go down, unless we're talking about some certain types of bonds, but that's later on. A loan, it will always. All right, so now let's look at some equations that these represent. I'm going to erase this because it is a lot, but we're going to just kind of go down the list and look at each individual one. So the loan amount, you don't really need to know much about the loan amount. Just know that it is the outstanding balance at time 0. Other than that, you just kind of use the loan amount in certain equations, but you never actually, it doesn't really have any equations for itself, other than like, obviously, the loan amount is going to equal the payments. Logically, the loan amount is going to equal the present value of all the payments. Keep that in mind. Very basic, very standard. All right, so the OB, or the outstanding balance, has a couple equations that you can use to solve it. There is one called the prospective method. The prospective method, which in turn, like prospective meaning you're looking in the future, is an easy way to remember it, and it is simply the outstanding balance at time t is going to equal the present value of all the remaining payments. That's the prospective method, because you're looking into the future. You're looking at all the future payments that are like left for me to pay. That's how you can calculate the outstanding balance at that point in time. And then there is the retrospective method. The retrospective method is the exact opposite of the prospective method. It works by looking backwards. So we accumulate the loan amount to whatever amount of time that we're at. So if t is 10, we accumulate L10 to the time 10, and then we subtract off the final value of all the payments that we have paid. We accumulate the loan amount to the time that we're at, and then we subtract the final value, or the future value, of all the payments that we've paid through that time, and that'll give us the outstanding balance. Those are our two main ways of finding outstanding balance. These equations are very important, not in the sense of the question is going to ask you to like find the outstanding balance. It's more so you're going to have to solve for the outstanding balance in order to get to another point in the question. Like, so if it's like, it'll be like, what is the payment? No, I don't know. I can't think of one where you would find the outstanding balance, but there are questions where you more so have to find the outstanding balance to use in another equation to get the answer, rather than just finding the outstanding balance. These two are very important. So now that we have the prospective and the retrospective method, these are our two ways of calculating any outstanding balance of a loan. Now we need to look at equations for interest and equations for principal. All right, so we got principal paid and interest paid. I'm going to do them together because they both have very similar formulas. The principal paid is going to equal the payment times v to the n minus t plus 1. Pretty simple. This is just kind of how you would calculate p. If you have the variable, like, yeah, you understand. This is one of the equations, is how you could calculate p. And then interest paid is going to equal r times 1 minus v to the n minus t plus 1. You can see they're very similar formulas, and they're like really easy. So these are two of the equations that you can use to find principal and interest, but there are some other equations that you can use that are more so just like general purpose, kind of like what they actually represent rather than equations that you would use. So the principal repaid is going to be the payment minus the interest. This is because when you're paying off a loan, your payments always pay off the interest that has accumulated before it reduces the outstanding balance. The principal repaid is what you are reducing the outstanding balance by, so it's what's left over of the payment after you pay off the interest. The interest is also going to equal the interest rate times the outstanding balance of the previous period. This is pretty self-explanatory. If you're at time 2, to get the amount of interest that you need to pay off for the third payment is the outstanding balance at times 2 times I. Very self-explanatory, I feel like. But yeah, these are our main equations. Now there is another equation that you can use, and this is an equation to find the relationship between the principal payments. Like, so if you say you're given an interest rate and you're given one principal payment, you can then find all of the principal payments by using this equation. So the principal at t plus k is going to equal the principal at time t accumulated k years or k periods. So this is very, like, once you know that this is a rule. It's very self-explanatory. You literally just accumulate. You can accumulate or you can discount any principal payment and get that one, like the value of the other ones at the different times. Very useful, but very simple. So yeah, so those are all of our equations for loans. Loans are very simple. I enjoy doing loans. They just makes a lot more sense. Loans and bonds, they make a lot more sense in my brain. I don't really know why. I think it's just because now we have these equations accessible to us that we can use. As compared to an annuity, you only have the annuity stuff. But that's pretty much it for loans. There are like some subcategories of loans where a loan can have a balloon payment or a drop payment. Basically, this just means that the very last payment is going to be different than all the previous payments. So in turn, it would be an annuity. If say you have a drop payment, or say you have this payment, it's going to be an annuity of payments plus R star discounted back, because R star is going to be slightly different than all the other ones. And then a drop payment is going to mean that the final payment is smaller than the other payments, and then a balloon payment is that the final payment is larger than the other. Pretty much you would do an annuity of all the payments prior, and then that very last payment you would have separate, and you would just discount it back to find the present value. But yeah, that's pretty much a balloon payment is pretty much the introduction to a bond. All bonds are pretty much a loan with a balloon payment. Besides, I'm pretty sure, so like all bonds, I personally think of all bonds as literally just a loan with a massive ass balloon payment. Keep that in mind. I'm not going to show you how to do a balloon payment because it's pretty self-explanatory. You just take one off, take the last payment off the annuity, and then it's just the annuity plus R star V to whatever N and plus one is, or whatever the annuity length is plus one. So that's loans. So let's look at some practice problems. So our first example here, a $3,000 loan at 18% per year is being repaid in 10 level payments starting 1 year from today. Determine I6. As always, we're going to start off with our timeline. So we got our timeline set up. A $3,000 loan, so that means we get $3,000 at time 0, and we are paying off a level payment of X at every single time starting 1 year from now. So this is what our time diagram looks like, and in a sense we are trying to find the interest portion of I6. We were trying to find the interest portion at I6 or time 6. So that means we are going to need the outstanding balance at time 5, because we are then, I'm assuming, since we are given the interest rate and the outstanding balance at time 5, or the interest rate and the loan amount, and we can easily solve for the payments here. I'm assuming the easiest way to go about it is to just solve for the outstanding balance at time 5 and then multiply it by the interest rate to get the amount of interest for I6, or to get what I6 is. So that's kind of what I'm representing on our time diagram here. Is these are all of our important dates, just kind of 1, 2, 9, 10, just to kind of get the scheme of what's going on here. The annuity of minus X every single time, and we're getting a $3,000. We're getting $3,000 initially at time 0, and then I added in 5 and 6 just because 6 is the time that we're looking for, and then 5 is another important time that we're going to calculate out because we're going for the outstanding balance at time 5. So now the first thing that we need to do is, no matter what, either the prospective or the retrospective method, since we are going to find the outstanding balance at time 5, the retrospective or the prospective method, they both need what the actual payment is. They both need R. So we're going to quickly find what R is using an annuity. So we know $3,000 is going to equal RA 10 because it's an annuity immediate. Our payment is 1 year after time 0. So it's an annuity immediate. This is going to solve for the annuity at time 0, or all for, it's going to solve for minus X at time 0. I realize now this is kind of bad. I wrote X in the time diagram, but it should be R. So just kind of every time you see X in the time diagram, just think of R. And then it's going to be at 18% per year, which is absolutely insane. What is this? So if you divide 3,000 by A angle 10 at 18%, you would get that R is equal to 667.54. So this is our payment. We're going to be paying off $600 every single payment. So yeah, now that we know what R is, we are actually able to then calculate I6 pretty much directly. Actually, we don't even need the outstanding balance at time 6 now that I'm thinking about this, but that is a way that you could solve it. You could use this to then find the outstanding balance at time 5. However, now that I'm realizing that we have R and we know what I is, we can simply just do this. If you remember before, I of t is equal to R times 1 minus V n minus t plus 1. That's what I put in here. Remember, do not round this answer. This is just rounded so I could write it on the whiteboard. Do not round the answer. That's exactly why I wrote R right here instead of this. I wrote R to signify you go into your calculator and you get what R actually is rather than the rounded value. So if you just put this into your calculator with V being 18, like V with an 18% yield rate, you put this into your calculator, you would then get that I6 is equal to 375.75. So doing this method, you would get that I6 is equal to $375.75. Yeah, pretty self-explanatory. If you were to go the other route and use R to find the outstanding balance at time 5, you could either do that through the retrospective method or the prospective method, because we know the interest rate, we know the payments now, we know what the loan amount is, we know N, we know all the things. You can solve for the outstanding balance at time 5 and then multiply that by 18% to get this. Just me being me, I was like, oh, we have R now. We can now do this. So that's what I did because that was technically the fastest way to do it. But so that's a basic loan problem. Let's look at another one here. So a $20,000 loan is being repaid by annual payments at the end of each year for 12 years. If 1 plus I to the 4th is equal to 2, find the outstanding balance after the 4th payment. So this one's pretty simple. We're going to start off with our time diagram. I'm not going to lie. I'm just going to do this because we only care about this loan for the first 4 periods. Like we don't really care about anything. So we're getting $20,000 right here, and we're paying back, we don't know, we're paying back X at the end of each year all the way up until year 12, where we also pay off X. And we are trying to find the outstanding balance after the 4th payment. So this is going to be OB4. So now just kind of thinking, we need to find OB4. We have technically the interest rate for OB4, or for 4 years, like what we can accumulate. If you think back, all of the outstanding balance equations we know uses R. Luckily enough, we can actually calculate R. But first to do that, we're going to need to calculate I. So if 1 plus I to the 4th is equal to 2, we would put 2 to the 1/4. So this equation implies that I is going to equal 2, I don't know how you would say this, a square root, but like to the 4. I don't know, 2 to the 1/4 minus 1, that's going to equal I. So if we put this into our calculator, we get that I is roughly equal to 18.9207%. So now that we have I, we can calculate R using just what we know about a loan, the value of a loan. So using our equation for a loan, same thing that we did in the previous problem. We're just going to divide 20,000 by A angle 12 at I. Remember, go into your calculator and get this actual value. Do not insert the rounded one. So if we do that, we get that. If we divide 20,000 by A angle 12 at I, we get that R. We get that R is going to equal 4,324.73. Approximately. Remember, it's rounded. So now that we have that, we can either do the retrospective or the prospective method to calculate this out. I'm going to use the retrospective method because it gives us what the accumulated value, or what the accumulation function for 4 years is going to be. So that's going to make accumulating L 4 years a lot easier. So this is the equation that we're going to use. L accumulated 4 years minus the future value of 4 payments. So if you were to just plug this into your calculator, you would end up getting, so if you put this into your calculator, you will end up getting that the outstanding balance at time 4 is going to equal about 17,142.86. That's a little bit more in-depth one. For here, L is 20,000. This one you can just plug in 2, so this becomes 40,000 minus R, and then accumulated for 4 years. This one is a little bit harder than the previous one we looked at, but still very easy, very basic loan problem. So we're going to look at one more here. So I just kind of want to show the relationship between different principal payments. So a 5-year loan has level payments at the end of each year. At a 5% interest rate, find P4 if P2 is equal to 80. If we start our time diagram, we're going to start at time 2, bring it to time 4. So our principal, I'm going to write it in terms of outstanding balance. So here we are lowering outstanding balance by 80. We are looking for what we are lowering our outstanding balance at time 4. Cool. So that's our time diagram. The easiest way to go about this would be to set up this equation. We're going to be using this equation. If we just sub it in, P4 is going to equal P2 1 plus I squared. And we know what I is. I is equal to 5%. So if we just put 80 times 1 plus 5% squared to our calculator, we'll get out P4, which is P4 is going to equal 88.2. So this is a very, very easy problem, but this just kind of shows you the relationship between the different principal payments. In a sense, that's pretty much loans. Loans are very, I think loans personally are the easiest part of the course, because after you learn time value of money and after you learn annuities, loans are pretty much an annuity. They follow the same concepts. They're pretty similar. They're almost identical. Like when I think of a loan, I think of just an annuity. And then the only extra part about loans is you have to know the automation schedule, pretty much, where you have the principal payments, how to calculate interest, how to find payments, like how to find how much each payment is. And then if you do get a question with a balloon payment or a drop payment, you have to then calculate that out, just kind of knowing what it is. But it's very simple. It's very, as you can see, it's very along the lines of annuities. It's very I feel like after you learn annuities, it's very common sense, most of this stuff. Yeah, that's loans. Let's move on to bonds. Alrighty, so now that we learned about loans, we can actually learn about bonds. Bonds are very similar to loans. I like to think of a bond as being a loan with a massive balloon payment. Kind of works better in my mind like that. They follow pretty similar lines, where it'll be an annuity and then one final payment at the end, which will be greater than all the other ones. These payments are going to be called coupons, so we'll just get into all the notation, and then that'll kind of help explain what's going on here. RIP the black marker. These are our 6 main things. I don't know the variables, but P is going to represent the price of the bond. So this is going to be the present value of the bond, or this is going to be what would be equal to the loan amount, or L. F is going to represent the face amount of the bond, and this usually, this is just face value. It kind of determines the coupon rate. Also, in a sense, don't quote me on this, but I don't think it for sure determines the redemption amount. But I know the redemption amount is based on it. Like if it's $1,000, if a bond has a face amount of $1,000 and it's redeemed at par, it will be redeemed for $1,000. R is going to represent the coupon rate, and this is going to basically determine how big of a payment we receive each year for the bond. Because if you look at a bond structure, I'll just draw a timeline of what a bond structure would look like. So if this is our bond time diagram here, we're going to be getting payments of, for example, 10 like this, and then we would also receive the redemption amount. So we'll just say 100 at time 10. So at time 10, we're still receiving that very end coupon, but we're receiving an additional amount of whatever the redemption amount is. R is going to determine how big these coupon payments are. And the way that we would determine that would literally be FR is going to equal the coupon payment. or the face amount times the coupon rate. F times R is going to equal the coupon payment. So in this sense, if it was a $1,000 face amount bond, it would be a 1% coupon rate to get $10 to be the coupon. And then the redemption amount is going to be how much it's redeemed for, or this final value. So in this example, it's C is going to equal 100 because we're getting an additional $100 for the redemption of this bond. Now, the redemption amount also has a notation of K, and K is just going to mean the present value of C. So in other words, it means C discounted back to time zero. And this is literally just to kind of help with notation, or not notation, like memorizing equations and whatnot. It's kind of cool. When we get into the equations later, it'll make a lot more sense, but K is literally just to kind of help memorize stuff. But yeah, and then like always, we have I. It's going to represent a yield rate instead of an interest rate. However, you treat them the exact same. In terms of how the math works out, there's not really a difference. And then N, like always, is going to represent the number of periods. So in this example, N is going to be 10. But yeah, so that's all the notation that we have for bonds. Let's get into some of the equations. All right, so I'm going to teach you the main 3 forms, or I guess it'd be the main 2 forms, and then stuff about them but like the sub parts of them. But there's I'm pretty sure Infinite Actuaries, they teach 3 different types of ways of finding the price of a bond. I'm only going to teach you 2. The third way they teach you is really just kind of like a shortcut way, and it's very specific to how you would it's a very specific usage case. Like, you're not going to be able to apply it in every problem. However, these other ones you probably will be able to apply in every problem. This one, like the third one, is literally like if you see a bond that is set up in a very unique, specific way, you can use this formula to get it a lot faster. But I don't really care about that. I never used it, so I'm not going to show you guys it. So our first formula that they're going to teach you, so to calculate the price of a bond, the first ever formula they're going to teach you, and the common sense formula they're going to teach you, is FR, or the coupon amount, and you're turning it into an annuity, and then you're adding the redemption amount discounted back at time zero. Very simple. Present value of annuity plus the present value of the payment. Very simple. And then the reason that we say that this is K is so that we have this. What does that say? Frank. The Frank equation. Look at that. It's the Frank equation. That's literally the only reason why we denote this as K, is so we can say Frank. Pretty cool, but really easy to remember Frank, so memorable guy. So that's the very basic one. That'll kind of apply to anything. You can use this, and it'll give you the price. But there are some other ones. So, for example, this is just a different form. Not a different form. This is a different way of calculating the price. I'm going to write it over here. So this is another way of calculating out the price. This works specifically if the bond is priced at par. And what's going on here is we have the actual redemption amount plus a coupon payment minus the redemption amount times the interest rate. And then we're taking the present value of an annuity, with that being the payments. It is another way of calculating the price. It's this equation is mainly going to be used for when the price is equal to the redemption amount, or the bond is bought at par, which means that the redemption amount is equal to the price. So technically, if the bond is priced at par, that would mean FR and CI are going to be exactly the same. So it's literally just going to be P is equal to C. So that's kind of where this equation comes from. It's pretty useless. I'm not going to lie. You never really use this, but you do use it to get other ones. So like this equation in of itself doesn't really give us much, because it's literally just telling us P is equal to C because the bond is priced at par. But if we were to move things around, we would get P minus C. All right, so hold up. Let me rewrite all of this actually. So I just kind of did some organization here. So this is what we were looking at before. P equals C, and it's priced at par. That's what the equation means. And then from this equation, though, we are able to do this. You would use this form if the bond is priced at a premium, which means that the price is more than the redemption amount. And then this will calculate the amount of premium. And this is very helpful because P minus C is the amount of premium, FR minus CI, and then like the present value of that as the payments. That will also give you the amount of premium. From the amount of premium, you can then calculate out a whole bunch of other shit. Pretty much, this is the equation for if there's a premium, if the bond is bought at premium, and then if the price, if the bond is bought at a discount, just like how if it was bought at a premium, you would use this, and this would determine how much premium, or like the amount of premium that it was bought for. The amount of premium. This is the same ideology as the premium, besides with a discount. If you bought the bond at a discount, this is how you would calculate out the discount of the bond. From calculating that out, you'd then be able to calculate the price or whatever you need, like the redemption amount, depending on what the question asks for, what the question gives. You are then able to calculate out pretty much everything here. But yeah, these are like the main equations for pricing a bond. If it's a par value bond, the Frank equation, premium and discount, those are the main ways of pricing. But then other than that, there's not really too much else towards bonds except for the same thing with loans. So same thing as for bonds, you can do the same thing and set up a automation schedule with a bond as you would with a loan. Besides, the equations are slightly different. Like if you remember when I was talking about loans, the retrospective and the prospective, they're the same ideology as you either look at all of the previous, like you accumulate the price of the bond up and subtract all the previous payments, or you look into the future and take the present value of all the future cash flows. It's the same ideology, but again, they're slightly different because the structure is slightly different. And then a lot of the other equations, though, will apply still. We'll just get into them. All right, so we're going to start off with the book value. Now, the book value is literally the outstanding balance. Besides, it's called the book value when dealing with bonds. Same ideology. Same ideology. BV0 is going to equal the price of the bond. It'll also have the same exact retrospective and prospective methods into calculating the book value. If you remember what the prospective method from the loan section was, it was looking into the future. So it was literally just taking into account taking the present value of all the future cash flows. That same ideology is going to happen here, where it's going to be the book value at time t is going to equal our coupon payments, the present value of our coupon payments. So it's going to be the same ideology. Besides it, we now have to account for the redemption amount of the bond. So the book value at time t is going to equal the present value of the coupons, which the time would be n minus t, because that's the remaining amount of payments. And then we would discount the redemption amount back to time t. So yeah, pretty self-explanatory. It's the same ideology, besides you have to now account for this redemption amount. So now if we look at the retrospective method, the retrospective method is going to be the exact same. Retrospective is going to be the exact same thing pretty much. Besides, instead of the loan amount, I guess it would be, never mind, I lied to you guys. It would be the exact same thing, because I was thinking it'd be different because the loan amount is not the price, but it is. The loan amount is the price of the loan. So this is the retrospective is the exact same. I guess the only difference is now instead of a loan payment, you are taking a coupon payment. You're subtracting off the coupon payments rather than an actual payment of anything. So, but yeah, that's book value. Book value is very similar, as you can see, very similar to outstanding balance. I literally think of them as the same exact thing. Fun fact, even on my exams, I tend to write out OB instead of book value because I don't realize that I'm doing it differently. But it doesn't really matter because it's just notation. As long as I actually know the difference, it doesn't really matter. But then obviously another really easy one is going to be, if you guys remember same thing with the outstanding balance, the book value at time t is going to equal the previous book value minus the principal. Same ideology. It follows the same thing as like a loan automation. It just has this big payment at the end. Now let's get into the other equations that we need to know. But yeah, this is all the book value ones. Very similar, very easy. It is basically identical to outstanding balance and loan automation. So, all right. So now if we look at, we're still gonna have PT represent principal repaid. However, in this, the principal repaid is going to be slightly different. The principal repaid in this is going to be slightly different than the other ones, but it'll be like the same thing as book value, where it's very similar to the loan version, besides it's slightly different to now account for a bond. So starting off, we're going to have PT is going to equal, so if you remember before how if we had a principal payment, it was equal to the payment v to the n minus t plus 1. We have that same ideology going on here. Besides, instead of using the coupon payment, we're going to be using the coupon payment minus the redemption amount times the interest rate, and then that is going to be our sub in for what would have been R if we were talking about a loan. And then PT is also going to equal the coupon payment minus the amount of interest. Just like if we were talking about a loan, it'd be the payment minus the interest and whatever left over goes down to diminishing the outstanding balance. Same thing here. So you get the coupon payment, it pays off the interest first, and then the rest of it goes into going into the book value, whether that be putting more into the book value, taking away from the book value. Kind of depends on how the bond is priced. All that matters is that no matter what the coupon payment goes into the interest, and then whatever left over, this equation is the principal, and then that is either added or subtracted to the book value. And then, like before, there is the same way of finding principal payments based on previous principal payments, or principal payments finding a previous principal payment from a future principal payment. So, and it is the exact same equation. If you want, so say in like our loan example that we used, if we wanted the principal payment at time 4, and then we were given principal payment at time 2, it'd be the principal payment at time 2 accumulated 2 years to then make it time 4. Pretty simple, pretty self-explanatory. And now if we look at the interest, so IT is going to represent the interest portion of everything, and same thing here, like in the principal, the same thing as a loan. The only difference besides the interest in a bond versus a loan, just like before though, the interest is going to equal the interest rate times the previous book value. The only difference that this interest does not have an equation like this. As before with the loan automation, you could have IT would equal R times 1 minus V n minus T, V to the n minus T plus 1. There is no equation like that can properly represent the interest paid and hold true like throughout all of them. And it's because the book value has this redemption amount, and it's kind of like doesn't really work. Just different structure, so that equation doesn't really hold. These are all of our principal and interest automation stuff. That's pretty much all the equations for bonds. Now, there are different types of bonds in of itself. So there is a thing called a zero coupon bond. Literally just means it is a lump sum of money that you receive at some point in time, or it is literally just the redemption amount. There is no coupons, so there is no annuity. It is literally just a lump sum of money at one point in time that you would then discount to whatever point in time you need it. So if it's a 5-year, say it's $1,000 5-year zero coupon bond, and 5 years you get $1,000. That's all that bond is. You just discount $1,000 back 5 years to get the price of the bond. Very simple. And then there are such things as callable bonds. Callable bonds are bonds that are callable, or you can get the redemption value before the bond actually truly is meant to be redeemable. And we'll work on a problem with it. Just know that there are such things as callable bonds, which change the duration of the bond, but it still is the same thing of the FR is still going to be the coupon payment, C is still going to be the redemption amount. The redemption amount might change if you call it early, but it's still going to be the redemption amount. Yeah, it's going to be the same structure as the bond, just called early. So that's all the equations for bonds. So that's pretty simple, pretty easy. Let's look at some problems. So our first example here, what is the price of a $1,000 face amount bond with a 8% coupon rate compounded semi-annually that is redeemable at par in 10 years if there was a 9% nominal yield rate convertible semi-annually? The face amount of the bond is $1,000. The coupon rate is 8% compounded semi-annually. It is redeemed at par, so it is redeemed at the face amount, or $1,000. It has a 10-year duration, and the nominal yield rate convertible semi-annually is 9%. We're going to start off strong like we always do. So we're starting off with our time diagram. I'm going to just immediately go to 20 and count the periods as half years. Because we're going to be counting in half years. So this is our time diagram. We know it's going to redeem at par, so we're going to get $1,000 right there. It has a 8% coupon rate compounded semi-annually. This would mean we are getting a total of an 8% coupon rate. In a year, we are getting 8% of the face amount. So what's happening is a way that we could do this is we can multiply 8% by 1,000 and get 80, and then divide it by 2 to get 40, and then that would be the coupon payment per semi-annual period. Or we can just divide the coupon rate by 2 because it's compounded semi-annually, and then multiply that by the face amount. I'm just going to do that. 8% divided by 2, and then multiply it by the face amount. And this is going to equal 40. That's just going to represent FR. That's how we would calculate that because it's compounded semi-annually. So now that we know what these coupon payments are, we can fill them in our time diagram. And we need to calculate the price of this. So let's just start off by I'm going to use the Frank equation because it is the GOAT equation. We love Frank. So that's going to be, so I got our Frank equation written out. Let's fill it in. All right, so we got it filled in, and now just to check to make sure we don't have to do anything with the yield rate, it is a 9% nominal yield rate convertible semi-annually. So that means that we literally just have to divide 9% by 2 to get 4.5%, and then that'll be the interest rate. So kind of write that to signify that the interest rate is 4.5%. So if you were to put this into your calculator, you would then get out that the price of this bond is going to be $934.96. Yeah, so that's the price of this bond. Very easy. As you can see, it's pretty much the same exact thing as before. If you just write out this, as long as you know how to do the time diagram, you can easily see that it is a $40 annuity for 20 periods, and then you just have a big lump sum of $1,000 that you need to discount 20 back. So yeah, that's the price of the bond. Next question. All right, a $1,000 face amount bond pays semi-annual coupons at an annual nominal rate of 8% and will mature in 3 years at par. The bond is purchased to yield 6% convertible semi-annually. Calculate the amount of premium. So first things first, we're going to start off with our time diagram. We got our 6 payments over the 3 years, semi-annual payments. It is redeemed at par, so that means at times 6, we are going to get an additional payment of $1,000, and then if we calculate out FR, which is going to equal 1,000 times 8% divided by 2, because we're doing semi-annual payments, so 8% divided by 2, which is going to equal 40. So our payments, we have payments of 40 at every. So we got payments. Our payments of 40 are now added to our time diagram. And then we need to calculate out the premium. So the premium, there's numerous ways of calculating out, if you remember. This is our equation that we have for calculating out the premium. The premium is going to equal P minus C, and it's also going to equal the coupon payment minus the redemption amount times I times AN. We can either calculate out the price and then just subtract that from the redemption amount, or we can just use this equation like straight up. So I'm going to use this equation straight up. So plugging in what we know, FR is equal to 40. C is going to equal $1,000 because it's redeemed at par. I is going to be 6% convertible semi-annually, so 6% divided by 2. And then this is going to give out $10 if you subtract, because it'll give 1,000 times 3% is going to give out 30. 40 minus 30 is 10. So then we do 10 A angle 6. A angle 6 at 3%. This is then going to equal $54.17. So the amount of premium that this bond holds is $54.17. Very simple way of calculating it out. I just kind of wanted to show you guys in this example that you can use, like what you can use these equations for, how you would use them. That's pretty much it for bonds. There's not really too much else on missing. Of course, we could do like an automation example, but that's pretty much the same thing as loans, so I'm not going to do that. Or we could look at a callable bond, but again, that's just the same thing as looking at a normal bond, besides the date moves up, so there's less periods. But yeah, that's pretty much all of bonds, a very general sense of bonds. Very simple, very similar to loans. If a loan had a balloon payment, that's kind of how I think about it. But yeah, bonds are pretty simple. They're not as fun as loans because they're a little bit more work and they're a little bit less intuitive. They are pretty simple and they are still pretty fun. So, all right. So for our next section and our final section, we have to look at duration and convexity of streams of cash flows. Yay. Alrighty, everyone. Welcome to the final section of financial mathematics here, immunization. So to start off with immunization, we have to learn duration. Duration, there's two different forms of duration, along with convexity, which we'll learn right after duration. There's going to be two forms of convexity. There's a modified duration and then a Macaulay duration. So yeah, let's get into it. The Macaulay duration is going to be denoted MACD. It's also worth noting that if a problem just says duration, it is referring to as the Macaulay duration. For duration, the Macaulay version of duration is like the go-to. It's the assumed one. So you would always assume Macaulay duration unless it says modified duration. Now, the Macaulay duration here is going to equal the derivative of the price with respect to the force of interest divided by the price with respect to the force of interest. Now, this is, I'm not going to lie, is a very niche case on how you would find the Macaulay duration, but this is truly what the Macaulay duration means. It is important to know there are questions that you will get that force you to use this equation, this relationship, but most of the time there will be another one that you would use, which is the Macaulay duration is also going to equal the sum of T times all the cash flows. So this would be, if it's say a 3-year loan or a 3-year loan, to calculate Macaulay duration of it, it would be 1 times the first cash flow, 2 times the second cash flow, 3 times the third cash flow, and then you would divide it by the price of that. So effectively, if we were to look at a timeline with this, or a time diagram. All right, so I got 2 time diagrams here. This one is going to represent what the actual cash flows are, and then this one is going to represent T times the actual cash flows. All right, so this is our actual cash flows. We have an annuity of payments with payments of 10 for 5 years. So then now if we multiply T by each of these cash flows, what we will get is, so as you can see, effectively, this formula becomes an increasing annuity. So if we just rewrite this, so effectively what we have is the Macaulay duration is going to equal T times that, like the cash flows for that time. Mind you, by writing CF, I mean the present value of those cash flows. It's not actually 1 times 10 and then 2 times 10 and then 3 times 10. But they're technically going to still be discounted back to times 0 because that's where we're analyzing this. The Macaulay duration just comes out to be an increasing annuity divided by P, or the price of the annuity. So this is a very simple way of finding the Macaulay duration. This is my favorite way of doing it because it is, in this case, it would be 10 times IA angle N, and then you would just divide it by 10 times A angle N, and that would be the Macaulay duration. Either way, this is how you would find the Macaulay duration. So then there is one more form of duration that we'll look at now. Mod D is going to represent the modified duration. So this is the duration. If the problem just says the word duration, it does not mean modified duration. It means Macaulay duration. So the modified duration is going to be pretty similar to the Macaulay duration in the sense of we're going to use the Macaulay duration to find the modified duration. So the modified duration is going to equal the Macaulay duration discounting back 1 period, or times V. That's the modified duration. There's no real way. Technically, if you want the true equation for this, it would be, if you wanted the equations for how to find a modified duration, it is you use the Macaulay duration, you find the Macaulay duration, and then you just multiply it by V. So there's no real trick with the modified duration. You just got to remember that it's the Macaulay duration times V, And these both are used in different approximations for, or both of these durations can be used for different approximations of the price depending on how much the insurance rate changes. Effectively, these durations are just measurements of the price sensitivity of that stream of cash flows. So it's worth noting what these durations are going to be used for. They're used or primarily used for predicting what the new price of a bond or loan or some stream of cash flows is going to be if the yield rate were to change. So yeah, let's look at those equations that would allow us to do that. So there's going to be an approximation for both the Macaulay duration and the modified duration, and they're both going to approximate pretty much the same thing, besides they're going to do it in their own little way because they both mean slightly different things. All right, just some quick notation before we get into these actual equations here. I0 is going to be the starting interest rate, and then I1 is going to represent the new interest rate. All right, so the price of the stream of cash flows at the new interest rate is going to roughly equal the price of the original price times the starting interest rate divided by the new interest rate to the Macaulay duration. So this is going to give a rough approximation of what the new price would be. It's worth noting that this estimated price will always be smaller than the actual price of if the interest rate were to change. That's the Macaulay one. You can also get like the percentage. So this would be referred to as the Macaulay approximation. So let's look at the modified approximation. So we actually have two approximations that we can use for the modified duration. This first one here approximates the change in price. So instead of the Macaulay duration predicting like the actual price, this will predict the change in price, and then you would then add or subtract that to the original price to get the new price. But it is the negative change in Y. So this is very important because this signifies the relationship between if yield rates go up, prices go down, or or in other words, like yield rates. If yield rates go up, prices go down. Yield rates go down, prices go up. So they have an inverse relationship. So that's kind of why the change in Y the change in I is negative, and it'll kind of keep it consistent. So if the change in P, so if you enter this into your calculator and the change in P is negative, you won't have to change it. It means that P is changing by a negative amount, like it's going down. Or in other words, the interest rate is going up. It's going to be the negative change in Y or change in I times the modified duration times the original price. So that's how you get the change in price. Now you can also estimate the percent change in price, which is literally going to be the same exact thing. The negative change in I times the modified duration, besides we are not multiplying it by the original price. So these are our approximations for our durations. So these are pretty easy. These are pretty self-explanatory. You just kind of do what you've done before with everything in here. You just plug in shit in the equations. So just like how the Macaulay duration is the price with respect to the force of interest, the modified duration is going to be the derivative of the price with respect to the interest rate divided by the price with respect to the interest rate. This is just kind of another relationship about the modified duration and how price works. So now we're going to look at mod C, or the modified convexity. And the reason I wanted to start off with the modified convexity this time instead of the Macaulay convexity is because, unlike duration, when the problem just says convexity, it is referring to as the modified convexity. As duration, if it just says duration, it's referring to the Macaulay duration. So you just got to keep that in mind, that these two are backwards. The modified convexity is going to be the second derivative of the price divided by the original price. That's just one way of calculating out the Macaulay or the modified convexity. And then the modified convexity is also going to equal. This is kind of where the calculating out the modified convexity gets really annoying and tedious. The modified convexity is going to be, it has the same ideology as the duration, where we are taking a weighted average, pretty much, where it is now weighted. It's going to be T times T minus 1 over M, and M is going to represent the amount of periods per year. If there's one payment per year, M is going to be 1, so it'd be T minus 1. If semi-annually, M is going to be 2. quarterly is for, So effectively, if it's a 1 year payment, what would end up happening is on like something like the 10th payment, it'd be 10 times 9 times the present value of the cash flow at times 10 times V squared. Very tedious, but yeah, then like before we have the cash flows, present value of the cash flows times an extra V squared. And then we're going to just be dividing it by the price again. Very annoying to do, very tedious. But the good thing is the SOA knows that this is a bitch to do. This sucks ass. Because there's no shortcuts at all that you can do. There's no real way to calculate, to have a formula that will increase by like T times T minus 1 over M. It's really not fun. Usually when the SOA has a question like this and you have to calculate out the Macaulay convexity, it will only be like 3 or 4 payments that you have to calculate out. So it is going to suck entering that in, but it will only be like 3 or 4. They're not going to make you do this over a 20-year semi-annual loan. It's just going to be 2-year loan with quarterly payments or something. I don't know. But yeah, that's modified convexity. So let's get into the Macaulay convexity, because the Macaulay convexity is actually pretty fun to do. It's so much more enjoyable than this. Just like how MACD represented the Macaulay duration, MACC is going to represent the Macaulay convexity. And the Macaulay convexity, if we follow suit with how the modified convexity works, the Macaulay convexity is going to equal the second derivative of the price with respect to the force of interest divided by the price with respect to the force of interest. So this is just one way of writing it. There's another relationship, kind of how like we've been having with all the durations in convexity so far. And then another formula for it. So this one is a lot easier. T squared times the present value of all the cash flows divided by the price. A lot simpler than T times T minus 1 over M. And then later on multiplying it by V squared. Yeah, this one's a lot easier. This one's a lot more friendly to calculate out. But that's pretty much it with the Macaulay convexity. Very simple. It's a lot easier to calculate out than the modified convexity, although the modified convexity is going to be the like primary used one. So Macaulay convexity. So before we get into actual immunization, I want to kind of show you how you would find the duration of, or the convexity of, an entire portfolio. So say you have 5 bonds that you invested in and you wanted to find the duration of all of like that entire portfolio, all the 5 bonds included. So this is how you would do it. All right, so I'm going to have X to know all of them pretty much, but it's worth noting that for this example, if you're trying to find the modified duration of this entire portfolio, you would only use the modified duration. If you're trying to find the Macaulay convexity of this entire portfolio, you would only use the Macaulay convexity. So just kind of keep that in mind, but I just wanted to have a general thing because they're all just weighted average. So it literally is just a weighted average, with the weights being whatever you're trying to calculate out. So the weight would be the duration or the convexity, and then the average would be of the prices. For example, if you have say you have a loan with duration 3 and a bond with duration 2, you would do 3 times the price of the loan plus 2 times the price of the bond divided by the price of the loan plus the price of the bond. So very simple. You literally just take a weighted average, and that's how you would get the duration or convexity of an entire portfolio. They all have the same exact thing. You just got to keep in mind, if you are dealing with modified convexity, you will get the modified convexity out. Like there's no interchanging them. And you also can't use both Macaulay, like you can't use the modified convexity as one of the weights and then the Macaulay convexity as another weight. You have to use all the same. So now that we're done with duration and convexity, we can actually get into immunization. So there's going to be technically 3 types of immunization. There's going to be the Reddington, the full immunization, and then exact matching. So we're going to start off with the Reddington. All right, Reddington immunization. All of these immunizations all do different things, but they all do the same thing. In a way, this Reddington immunization, it's going to protect the surplus from small charges in interest rate used to discount the assets and liabilities. So pretty much, basically what this is going to represent is if there's a small change in the interest rate, if you have a portfolio that is immunized, a Reddington immunized, it will stay true, as in the sense of your assets will always fulfill your liabilities for small changes in the yield rate. So that's pretty much what immunization does. It's you have assets, you have liabilities, and you are trying to have these assets. You're trying to find it'd be investing into assets that will then cover the liabilities that you have. Immunization just kind of ensures that through changes of the yield rate, you will still, like, those assets will still cover those liabilities. Starting off with the Reddington one, there's three kind of rules and ways that this works. Yeah, three conditions. So it's also worth noting that, like, when you're the way the questions are going to be for this Reddington immunization is going to be like, this portfolio is Reddington immunized or something. Find the modified duration of the assets, or it's going to say it, like, does this portfolio follow Reddington immunization, stuff like that. So there's going to be three conditions that you need to check to see if something is Reddington immunized. So the first one is going to be the price of the assets is going to equal the price of the liabilities. So this is pretty much just the present value of the asset cash flows are going to equal the present value of the liability cash flows. The second one here is going to be the second condition is going to be that the modified duration of the assets is going to equal the modified duration of the liabilities, or the Macaulay duration of the assets is going to equal the Macaulay duration of the liabilities. Now, you can use either or, it doesn't really matter, as long as you prove that one of the durations is equal to that corresponding version of the other set of cash flows. It's okay. So pretty much it's modified and Macaulay and Macaulay. You can't do Macaulay and modified. And then the third and final condition here is it's going to follow the same things as the second condition, where you can mix and match the Macaulays, but they have to be modified and Macaulay and Macaulay. It is that the modified convexity of the assets is greater than the modified convexity of the liabilities, or the Macaulay convexity of the assets is greater than the Macaulay convexity of the liabilities. Same thing with the condition 2, has to be modified and or Macaulay and Macaulay. You can't have one modified and one Macaulay, or it won't work. Yeah, these are our three conditions for Reddington immunization. Very simple, and it's kind of just, you'll be given a kind of portfolio of cash flows, some liabilities, some assets, and then you would then analyze those cash flows to see if these conditions are met. If they are, it is Reddington immunized, and it will protect against small changes in the yield rate. Yeah, that's pretty much Reddington immunization. So let's get on to full immunization. So the full immunization is pretty much the same thing as the Reddington immunization, besides it's a little bit better, as the Reddington immunization only covers for small changes in the interest rate or in the yield rate. The full immunization will protect against any change in the yield rate. If you are able to achieve full immunization, your assets, no matter the change in the yield rate, will always cover your liabilities. That's why full immunization is a little bit better, although it is a little bit harder to achieve. So let's look at the conditions. Same thing as Reddington immunization. They have three conditions. So the first condition is just like the Reddington one. The price of the assets have to equal the price of the liabilities. And the second condition is the exact same too, and being the modified duration of the assets needs to equal the modified duration of the liabilities, or the Macaulay duration of the assets needs to equal the Macaulay duration of the liabilities. Just like before, it has to be modified or Macaulay and Macaulay. You can't have one of them being a Macaulay duration and the other one being a modified duration. It will not work. The third and final condition is where they start to differ. So the third condition is going to be that there is an asset cash flow before and after every single liability cash flow. So this means that if you were to draw a time diagram of all the cash flows in that portfolio that you're trying to immunize, it will always go asset liability, asset, liability, asset, liability, asset, liability, that type of ordeal. There will never be two liabilities next to each other in that sense. And then it's also worth noting that if something is fully immunized by just common sense, since the full immunization protects against any change in the yield rate, if it's fully immunized, it will also be Redington immunized, because the Redington immunization protects against small changes, full protects against all changes, so all includes small. So if it's fully immunized, it is Redington immunized. So fun fact, if it's asking you if it's Redington immunized and you notice that the durations are equal, the prices are equal, and there's an asset cash flow before and after every single liability cash flow, you can just automatically assume that it is Redington immunized without even calculating out the convexities to ensure that that condition is true, because it'll fall under fully immunized. So yeah, that's pretty much fully immunization. Full is a lot easier to calculate out than Redington because you don't actually have to calculate out the convexities. I really like calculating out full immunization. It just kind of makes me happy. I don't know why, but it does. So we're going to look over that third type of immunization, which is going to be exact matching, or in a sense, every single liability cash flow that you have a asset cash flow to exactly match that liability. So yeah, I don't really know. There's not really much to write down about exact matching. It is literally right in its name. Every single liability cash flow that you have, you will create an asset cash flow to exact match that liability. So say if you have two liabilities cash flows, one in a year from now that's $100, one in 2 years from now that's $200, you would invest in two asset cash flows, one that gains you $100, or no, you would invest in one that would gain you $200 at year 2, and then hopefully that one that you invested in to $200 gives you one back, like a payment of some sort for year 1, so then you don't have to invest as much into year 1. But either way, at those point in times, you are literally just exact matching the values. So if you have a liability cash flow of 200 at time 2, that means your asset cash flow at time 2 is going to equal 200. And then it's that same exact thing for every single liability cash flow. There's not really too much to write down. It's kind of just in these sort of questions, they'll give you liability cash flows, and then they'll give you certain types of bonds that you can invest in, whether they be zero coupon bonds or bonds with coupons. Then you would see how much of each bond you would buy in order to exact match all the liability cash flows. It's very simple. It's honestly my favorite thing to do in all of exam FM. I really can't tell you why. That and full immunization, I just get really happy when I do them. Don't really know why, but they're hype. They're really fun. So yeah, that is the entirety of a very, very basic introduction into all of the kind of stuff that you need to know for Exam FM. So we're going to end it off here with a couple questions, some practice questions about duration, convexity, and immunization. So let's start off strong. So this is a pretty good example of what they would ask you if they wanted you to find the modified duration for something. This just looks at one singular set of cash flows rather than an entire portfolio, so that kind of makes it a lot easier for us. A $1,000 face amount bond pays semi-annual coupons at an annual rate of 6%. This bond will mature in 2 years at par. This bond is priced to yield 8% convertible semi-annually. Find the modified duration. So just kind of looking at this, to find the modified duration, we can do two ways. We can take the derivative of the price with respect to I, since we were given that, so we could take the derivative and then divide it by just the normal price, or we can find the Macaulay convexity and then change the Macaulay convexity based on multiply it, like discount it back to get the modified convexity. But either way, what I'm noticing is that we are going to have to find the price of this bond no matter what route we go. So I think that is going to be where we start. So let's start off by just solving for the price. So the price of this bond is going to equal, all right, so this is our equation that we got for the price of the bond. It is FR, which is the coupon amount, 1,000 times 6% divided by 2, because they're semi-annual coupons at an annual rate of 6%. So 6% divided by 2. So that is our like annuity, and then we're getting our redemption amount at par, $1,000, discounted back 4 periods, because that's 4 periods in total, 2 years of semi-annual payments. So this is our price formula. So basically what I'm going to end up doing is I'm going to calculate out the Macaulay duration and then convert it into the modified duration, just so we can see kind of how you would calculate out a Macaulay duration. But yeah, so if we were to put this into our calculator here, actually we technically don't have to put this into our calculator until the very end, so I'm not going to do that yet. But so since we are going to try to find the Macaulay duration, it is going to be, so if you remember before, it is a increasing annuity divided by just the price. So it is going to be, I'm just going to simplify FR, so it's going to be 1,000 times 3% or 30. So it's going to be, here, let me write it down a little bit more. So here is what our equation is going to look like for our modified duration, or Macaulay duration. Now, since I converted it into periods of 4 instead of semi-annual payments, so like what you could do is instead of 4 periods, you would have 2 and increase by 0.5 every time, because the durations and convexities are always in terms of years. Yeah, so if I were to just calculate this out, it would give me in terms of a scale of 4, but we are in 2 years, so we would have to divide it by 2. So that's why we're dividing it by 2, because they're semi-annual payments. So it's like we multiply the payments like n by 2, so we divide the Macaulay duration by 2. It's kind of just, you just got to know that the durations and convexities are always going to be written in 1 year intervals. Like it's always going to be with respect to t equaling a year. So if you change that, so say instead of semi-annual payments we had quarterly payments, it would then be n would then equal 8, and we would have to divide the Macaulay duration by 4 afterward. But since it's semi-annual, we are going to be dividing it by 2. And again, this is just how I personally like to think about it. This is how I go about solving problems. Makes a lot more sense in my head this way. But if you really wanted to, you could do things of 2, but then you wouldn't be able to take this, like you can do it in terms of time equaling what it actually equals. Besides that, I just feel like that's a lot harder, because then you're going to be dealing with time intervals of 0.5, 1, 1.5, and 2, rather than just 1, 2, 3, 4, and 5. You can simply just divide it by however many periods are in a year. I hope that made sense. But yeah, that's pretty much what's going on here. That's why we're dividing it by 2. It's because I doubled the amount of periods, so we have to divide it by 2 because we need it in terms of a year. Either way, it's going to follow the same ideology of, it's going to be the increasing annuity that we saw before, where since it's going to be t times the present value of that cash flow, it's going to be increasing by the payment every single time, and then it is going to be plus the redemption amount. And since the redemption amount is happening at time 4 in this case, it's going to be 4 times 1,000, or the redemption amount discounted back, and then of course we are dividing it by price. So if we were to put this into our calculator, all right, it's also important to note that the interest rate in this case for the periods I have here is going to be at a 4% interest rate, 8% divided by 2. I just kind of realized that as I was putting this into my calculator that we don't have an interest rate. So this is the interest rate. So if you were to calculate this out, you would get that the Macaulay duration, the Macaulay duration with the semi-annual payments being the periods, is going to end up being 3.8249, or just about there. I think I rounded it weirdly because I didn't want to rewrite it, but it's going to be around this number, and then you would divide that by 2 because we doubled the amount of periods, doubled the amount of periods effectively. So you get a Macaulay duration of 1.9125. Now that we have the Macaulay duration here, I'm just going to erase all this and rewrite like the Macaulay duration part. So now that we have the Macaulay duration is going to equal 1.9125. Now we just have to discount it back 1 period to find the modified duration. So now remember, do not ever round. Go into your calculator and get the actual value. If you discount this back 1 period, you should get about 1.8389 to be the Macaulay duration of this bond. Just like that, very simple. We calculated out both the Macaulay and the modified duration in this example. This is kind of like a very rough, this is pretty much how questions would be structured if they wanted you to find a duration like this. So yeah, pretty simple, pretty easy. As long as you know the equations and know what you're doing, it's pretty simple. But that applies to everything in life. So let's look at another one. So we got another problem here. A $500 face amount bond pays annual coupons at a rate of 6% per year. This bond will redeem at par in 3 years, and at a yield rate of 10%, calculate out the Macaulay convexity. So this is obviously a convexity problem. So if we remember, we're going to be looking at the Macaulay convexity. So if we remember what that's going to equal to. So if we remember what the Macaulay convexity is going to equal to, since we're given a yield rate rather than the force of interest, we can't really take the second derivative of the price function. We could, in a sense, convert the yield rate into the force of interest and then do it, but I think like that's about 10 times more extra work. So we're just going to be doing this formula here. T squared times the present value of the cash flow divided by the price of the cash flows. So like before, we're going to need the price of this bond. So the price is going to be our face amount, which is 500 times our coupon rate, which is 6%. We have a 3-year, year annual coupons. So a angle 3 plus our face amount, it is being redeemed at par. So our face amount discounted back 3 years. So this is our price function. I'm just put this into the calculator once we put all this into the calculator. But so now we need to determine what kind of like our cash flows are going to be. So for this problem, I'm actually going to draw a time diagram because I feel like it'll really help just kind of visualize what's actually going on here. 1, 0. So this is our time diagram. I'm going to write it in terms of the numerator for this. So it's going to be t squared times the cash flow at that point in time. All right, so we're going to have 500 times 6% is going to be 30. So we're going to have 1 squared times 30 here. Mind you, it's discounted back 1 period, but I'm just going to write it not discounted back. So this is kind of what's happening here with this numerator for the Macaulay convexity. It is going to be 1 squared times the present value of 30, and then 2 squared times the present value of 30, and then 3 squared times the present value of 30. So that's just kind of like our visual representation of what's actually going on here. So if we were to just actually kind of fill in this fraction. All right, so this is what our fraction is going to end up actually looking like. It's going to be 1 squared times 30v plus 2 squared times 30v squared plus 3 squared times 30v cubed. And then all that is going to be divided by the price, which is right here. So then we can simply just put that into our calculators and we'll get out a convexity. So before we actually do that though, I wanted to say if you were to calculate out the modified convexity in this case, instead of 1 squared, it would be 1 times 0 because it's t minus and then m is going to equal 1, so it's going to be t times t minus 1. So it's going to be, in this case, it would be 1 times 0 times 30v plus 2 times 1 times 30v squared plus 3 times 2 times 30v cubed. So it's very similar to calculating out the Macaulay convexity. It's just Macaulay convexity is a lot simpler because you just do whatever point in time that is and square it rather than doing it that point in time times that point in time minus 1 minus that point in time times t minus 1 over m. It's a lot easier to calculate out. But if we were to put this into our calculator, we would get, mind you, our interest rate. Again, I realize this as we're putting it into the calculator here, but our interest rate is 10%, so just kind of keep that in mind as you're putting it into your calculator. All right, so at time, as I was entering this into the calculator, I realized I made a crucial mistake. I forgot to include the redemption amount for when we were actually putting this into our time diagram. Everything's going to stay the same except for time 3, where we're getting the redemption amount. It's still going to be 3 squared, but instead of just 30, it's going to be 530 because that's how much money we are getting at that point in time. We're getting the face amount redeemed at par plus our $30 coupon payment. So we're getting $530 at time 3. Again, it really wouldn't change anything. It just is, instead of multiplying 3 squared, instead of it being 3 squared times 30 v cubed, it's 3 squared times 530 v cubed. All right, so if you were to put this into your calculator, you would then get out that this has a Macaulay convexity of 8.2401. Again, pretty simple. It's just a little bit more tedious. having to do the t-squared and all that, and there's not really a quick easy formula like an increasing annuity that you can use to easily solve it. You kind of have to type out every single one. Yeah, that's a Macaulay convexity example. Whoa, Mac-C, not Mac. Alrighty, before you head out, I just wanted to say thank you for watching. If you actually made it through this entire video, please comment your name and address. I would love to personally give you some sloppy toppy. But yeah, I just want to say thank you for watching. Again, this video shouldn't really replace any study materials that you use. This is more so just a kind of introduction. I wanted to show what I'm actually doing in my daily, I do have a passion for what I actually am pursuing in my personal life, and I just kind of wanted to show you guys a little bit of what I'm actually doing, like beyond just kind of like what you see on the screen. I wanted you guys to like kind of know what I would be doing on a day-to-day basis in regular occupation after I graduate. But yeah, so that's pretty much just a quick overview of Exam FM. Again, there's a lot more in-depthness and like detail that you need to figure out by yourself. This is a very, very surface level, just kind of introduction to it. Yeah, I hope you guys enjoyed. Thank you for watching.